Hello students, I welcome you again on PhysicsWallah in this Champions series for JEE and NEET. Okay, so today we will start a very brand new chapter, that is electromagnetic induction. Okay, this is the fifth chapter of electrodynamics, and here you will learn amazing relationships, amazing interconnections between electric and magnetic field, and that is why the name electromagnetic induction. Let us see what we are going to learn today. So we will start with magnetic flux and Faraday's law. Just like electric flux, we have magnetic flux here, and motional EMF. You will learn that when a conductor moves in magnetic field, some voltage is developed across it, and that is called motional EMF. Okay, and then induced electric field. These electric fields will be induced when there is some changing magnetic field in a region. Okay, and then we have self-induction and mutual induction. Self-induction actually is the new you can say is a brand new element to electrical circuits, just like capacitors and resistances, just like batteries. We have a new element in electrical circuits, and then we will learn circuits having induction. Okay, those we call LR circuits, and then we have mutual induction and LC oscillations. Okay, so let us start. The first point here is magnetic flux. Okay, just like electric flux, when some magnetic field lines cross an area, suppose these are magnetic field lines and they are passing through some area, we also call this area as an area vector, and here also area vector is defined as a vector in a direction perpendicular to the plane of the area. And here also, when the field lines cross this area, we say the flux is crossing that area, or the magnetic flux is crossing that area. Okay, and the definition of magnetic flux is equal to, here we call magnetic flux as phi b, or simply phi, and phi b is defined as integral of b dot dA, just like E dot dA in case of electric flux. Okay, so remember, whenever some field lines cross an area, there is magnetic flux associated with that area, and that flux is given by this relation. And also all the calculations are similar to the electric field calculations, the electric flux calculations that we did in the first chapter. Okay, so let's begin with our first question. And here we have a long straight wire carrying a current I naught, and close to this we have an area, or we can say we have a square loop of edge length B. The nearer edge is at a distance A from the wire, and we have to calculate the flux of magnetic field through this area. See, actually, if the magnetic field through the area is uniform, you could directly apply B times A, B times area, or B dot area. Okay, but as you know, the magnetic field of this current is variable as we move away from it. So in this region of this loop, we have a stronger magnetic field close to the wire and weaker magnetic field away from the wire, right? So what we'll have to do, we will have to select an area element like this. We can take this area element of any length parallel to the wire, because parallel to the wire there is no change in magnetic field. But as magnetic field is changing in this direction we cannot take bigger width. So suppose the distance of element from the wire is x, okay, and the width of element is dx, right? As you know, the current is going upward. If I take my finger or thumb in the direction of current and I point my fingers towards the element, curl my fingers, they are pointing inward. And if they are pointing inward, now we know the magnetic field of this wire is inward. So at the place of element, the magnetic field is inward, and as the thickness of element is very low, we can assume that magnetic field is almost not changing in this small width. Okay, so we can calculate very easily the tiny flux that goes through this area element. Okay, and that tiny flux can be written as d phi b equals the magnetic field at this point. So as I think you remember, the magnetic field because of the current at distance x would be mu naught I naught divided by 2 pi x, right? This is the magnetic field multiplied by area. I can see, I think you all can see, the length of element is b and the width is x. So we have b times dx, okay? And obviously the magnetic field and area can be taken as in same direction because magnetic field is in inward direction and you can take area vector also in inward direction. So we can forget about the dot product because both are in same direction, okay? And if you integrate this for all elements, you will get the net magnetic flux through that square cross section, square area. Can you see the first element will be here? And at the place of first element, the value of x would be simply a. So this integration will start with a, the value of x as a, and at this place where we have the last element, here, where we have the last element, here the value of x would be a plus b. So this will go up to a plus b, and that would give you the right flux through this area. Let's take mu naught I naught b upon 2 pi outside this integration sign, and we have dx by x here from a to b, a to a plus b. So this will become mu naught I naught b upon 2 pi, and I think you remember this integration is log x, okay? And after putting the limits, you will have log upper limit b plus a divided by a. Okay. So that is your flux through the cross section area. Okay, let's move over to the next concept. Let us now understand Faraday's laws. Actually, Faraday did an experiment purely accidentally, and there he observed an amazing phenomenon that a magnetic field, a changing magnetic field or changing magnetic flux can create a voltage source similar to a battery or almost identical to a battery. As a battery in a loop can create current, he said changing magnetic flux can also create a current. So changing magnetic flux is also a source of voltage. What he observed that when magnetic flux through a loop changes with time, an EMF or a voltage is induced in that loop, and this phenomenon is called electromagnetic induction. What he said, suppose we take a loop. And suppose we have a magnet here, magnet's north pole here. As you all know that the north pole emits magnetic field lines like this. So some of the line may not cross the loop, but few lines will cross the loop. They will contribute to flux through that loop. And suppose we move this magnet downward or upward. When we move this magnet downward or upward, the flux through this coil change. Because suppose we are moving this magnet downward, this line which is not crossing the loop may cross the loop and the flux would increase. If we move the magnet upward, this line which is crossing the loop may not cross the loop when it moves upward, and the flux through that loop would decrease. And when this change is happening, he observed that a voltage is present in this loop. How he observed? He applied a voltmeter, a sensitive voltmeter here, and the voltmeter was giving some deflection. So deflection means there is voltage or there is EMF in that loop, and this phenomenon he named electromagnetic induction. Let us understand it in a different way. Suppose we have a coil. We are taking a multi-turn coil because this would multiply the effect. And suppose we have a magnet here. Okay, this is north pole of the magnet, this is south pole of the magnet. If we switch on the magnetic field lines, can you see the magnetic field lines are entering some of the magnetic field lines are entering the coil. So this coil has some associated flux. Okay, and the one bulb is also connected to the ends of the coil. So if there is a voltage in the coil, if there is an EMF in the coil, just like battery, the bulb must glow. But what he said, whatever is the amount of the magnetic flux crossing the coil, there is no EMF. But when this flux changes, suppose I move this magnet, can you see? When the magnet is moving, the flux through the coil is changing. When I am moving magnet towards the coil, the flux is increasing. When I am moving the magnet away from the coil, the flux is decreasing. And when it is changing, whether increasing or decreasing, both ways, some EMF is induced and you can see the bulb glowing during that changing period only. Okay. As I am moving it slow, if I am moving it slow, the bulb is glowing very slowly. But if I move it really fast, the EMF induced is quite fast. Can you see that? The EMF induced is quite fast. If I also connect a voltmeter here, can you see when I am moving this magnet, when the flux is changing, the voltmeter is giving deflection. Right, the voltmeter is giving deflection. So this phenomenon is called actually the electromagnetic induction. Generation of electricity, generation of electrical voltage because of changing magnetic field is called electromagnetic induction. This can also be created by flipping the magnet. Why? Suppose you are taking the area vector of coil as this. This is the area vector of the coil, and can you see it this way, the magnetic field is also towards left. Also towards left. So we have approximately the flux as B times A. Just ignore for a while that flux is changing. The flux has different values at different times. Just imagine the magnet is big enough and the field is almost uniform over the cross section area of the coil. So the flux is B times A, because the angle between B and A is 0, the B dot A would be simply BA. But what if we flip the polarity? If we flip the polarity, suppose the south pole is facing leftward and north is facing rightward. Okay. Now the directions of these arrows will be flipped, and then area would still be towards left, but the B will be on the right direction. There will be 180-degree angle between B and A, and then the phi dash, the new flux would be minus BA, as the angle between B and A would be 180 degrees. So if I keep this polarity changing, the flux is changing here, BA minus BA, BA and minus BA, and then also you can see some voltage being produced here, the bulb glowing. Let us see how. I am flipping the polarity by touching this button, and can you see the polarity is flipping? This time the flux is plus BA, this time the flux is minus BA. So flux changed from plus BA to minus BA, and when the flux is changing, can you see the deflection in voltage? And the bulb is also glowing with a low brightness. Okay. So that was something about electromagnetic induction. When magnetic flux changes through a coil, an EMF is induced in that coil, and this is what electromagnetic induction is. Okay. Faraday, after many experiments, also told us that the induced EMF, the magnitude of EMF induced, is equal to actually n times the rate of change of flux through the coil. What is n? N is actually the number of turns in the coil. N is the number of turns in the coil. So if we have a 1-turn coil, we have to find E induced by simply calculating d phi by dt. But if we have a n-turn coil, the effect simply multiplies. So the E induced equals n times d phi by dt. If I put this n inside d by dt, we'll be having d by dt times n phi by dt, sorry, n phi. This term n phi is collectively called flux linkage and denoted by a Greek letter psi. This is psi. So this psi is called flux linkage. It is actually the total flux associated with all turns of the coil. So we can say it is the net flux, the total flux associated with the coil. So always remember, the psi is the total flux associated with all turns of the coil, and it is equal to n times the flux associated with one coil. Okay, so E induced is n d phi by dt. If you are changing a magnetic field slowly, flux is changing, but the rate of change of flux is less. And if the rate of change of flux is less, there will be less potential difference developed. And that is why when I was moving that magnet slowly, the bulb was glowing very slowly. But if you move that magnet with a high speed, the flux will change at a very high rate. A high EMF is induced, and high EMF if induced, and if high EMF is induced, you will get a larger voltage, larger induced EMF, and the bulb will glow with a bigger brightness. Okay. You can also improve the effect by taking a multi-turn coil as compared to a single turn coil. Okay. So this was all about Faraday's law. Later, after Faraday, Lenz improved this law. He observed that when some EMF is induced in the coil, a current also flows in the coil if coil is closed. If a current can flow, the induced current will also flow in the coil, and that current is called induced current. But he observed that the direction of induced current is such that it opposes the cause which is creating it. Means if a changing magnetic flux is creating induced current, the direction of induced current will be such that it will oppose that change of flux. Okay. So the law says the direction of induced current is such that it opposes the change that has caused it. And this law helps us to determine the direction of current in the loop. Let me tell you how. Suppose we have a loop like this. I've drawn half the axis. It shows us this part of the loop is outside the screen and this part of the loop is behind the screen. Okay. If we have a magnetic field downward like this, B, and let us say the magnetic field is increasing. Remember, the magnetic field is not causing induced EMF. The change of magnetic field, the change of flux is causing the induced electric field. Okay. So as magnetic field is increasing, the flux through this coil will also increase. And now some induced current will flow in it. Okay. When induced current will flow in it, it will flow in such a direction to oppose this change. Now you know, if magnetic field is increasing, the flux is increasing, the induced current can only oppose this increasing flux by creating an opposite flux. So induced current will flow in such a direction that it will create its own magnetic field, means its own magnetic flux. This you can call as B induced magnetic field because of induced current. And as flux is increasing, the induced magnetic field must be in opposite direction to the applied magnetic field, so that it can oppose the change, it can oppose the increase of flux. Okay, and this is the only way. So if the B induced is upward, the current in the loop should be like this. If current in the loop is like this, then only the magnetic field induced by that current can be in upward direction. So this is the direction of current induced, I induced. If you see the loop from above, you will see anti-clockwise current in the loop. Okay, let us understand it in more detail, how you find the direction of induced current. Simply remember one thing: if the flux is increasing, the B induced created by induced current will be opposite to applied magnetic field. And if flux is decreasing, the B induced will be in the direction of applied magnetic field. Let me give you one more example. Suppose we have a coil, a similar coil there, and there again we have downward magnetic field, and this time it is decreasing. Magnetic field is decreasing. If magnetic field is decreasing, means the flux this time will decrease, and if flux will decrease, induced current will oppose this decrease, means it will try to increase the flux, and the induced current can increase the flux if it creates its own magnetic field in the direction of applied magnetic field. This way it can oppose the decrease, it can help the flux increase. And if this is the direction of induced magnetic field, the thumb should be downward and current should be this like this. So current here is like this. If you see from above, you will see the clockwise current is going in the loop. Okay. So this is the method how you find the direction of induced current in a coil in which flux is changing. Simply remember one thing: if you ever see flux decreasing, always point your thumb opposite to the direction of applied magnetic field. Remember this law. Whenever you see flux decreasing, point your thumb in opposite direction to applied magnetic field, and curls of finger give you direction of current induced. Okay. But if you see flux decreasing, point your thumb in the direction of applied magnetic field, and curls of finger will give you appropriate direction of induced current. Okay. Let us practice few questions based on this. Okay. So we have 4 questions, and the purpose of all 4 questions is to find the direction of induced current in the loop. So in the following cases, using Lenz's law, we have to predict the direction of induced current. In the first case, can you see? In the first case, we have a loop in the plane of this screen, and we have an inward pointing magnetic field B. And the part says, and the question says B is increasing. If B is increasing, means flux is increasing. Okay, and if flux is increasing, always point your thumb opposite to the direction of applied magnetic field. As the applied magnetic field is inward, point your thumb outward, and the curls of finger will give you direction of induced current. So here the direction of induced current is like this. Okay, let's try this one. Here we have a constant magnetic field. In the second part, we have a constant magnetic field, but we have a ring whose size is expanding somehow. And if the size of the ring is expanding actually, then obviously the field is stationary, the field is constant, but the flux through the coil will definitely increase, because flux is magnetic field times area. The area is increasing here. And if the area is increasing, obviously if the flux is increasing, we will apply the same logic here. And if flux is increasing, I'll point the thumb opposite to the direction of applied magnetic field, means the field is inward, I'll point my thumb outward. And the curls of the finger will give us the correct direction of induced current. This is direction of induced current. Okay. Let us look at the third part. I'll suggest you solve these parts yourself, pause the video and then look for solution. Okay. As you know, we have a current carrying long wire here, carrying some current in upward direction. Can you see that? If current is in upward direction and we have a square loop placed very close to it. As the current is upward, I can point my thumb in the direction of current, and as you can see the fingers curl are pointing inward. So now we know the magnetic field here is inward. And this loop is moving with some velocity towards right. As this loop is moving towards right, I think you remember the field is stronger near the wire and it is weaker away from the wire. So actually the loop is going in the region of lower magnetic field. The loop is moving towards the region of weaker magnetic field. And as the magnetic field is weakening, the flux through the loop's area will definitely decrease. And if flux is decreasing, the induced current has to help the flux to increase, has to oppose the change. So as the flux is decreasing, it will try to increase the flux, and for that you have to point your thumb in the direction of applied magnetic field. The applied field is inward, point your thumb inward, and the curl of the finger will give you correct direction of induced current. So this is the direction of I induced. Let us try the last option, last question. Here we have a coil. This dotted line suggests that this part of the coil is outside the screen and this part is inside the screen, right? This is behind, this part is behind this part. And we have north pole approaching the ring. So since north pole magnetic fields are emitted, yes. And if north pole will approach the loop, obviously the magnetic flux would increase, because more and more lines which are not crossing initially this area will cross this area and the net flux would increase. As you can see, the field is towards left and flux is increasing. Point your thumb in the rightward direction and you can see the curl of finger is like this. The curls of finger are like this. So current in this loop will look like this, that is anti-clockwise if looking from this side. So current, it would be, the current, induced current would be in this direction. Okay. So that is all about the direction of induced current. Let us analyze a single loop in the changing flux situation. Okay. So suppose we have a current, a conducting loop actually. Suppose we have a conducting loop placed in magnetic field. Let us say magnetic field here is uniform, right? Uniform means the magnetic field is same everywhere. It is uniform or it is invariant with space. It is same at this place, same at this place, but it is varying with time. It is increasing with time. So B increasing with time, but not changing with position. It is same at all place. If it is same at all place, the orientation of the loop is perpendicular to the magnetic field. So you can assume the area vector is pointing inward. And if area vector is pointing inward, the B is pointing inward, you can write the flux as B times A. Isn't this simple? The flux is B times A. Let me tell you one more thing about Lenz's law. As Lenz's law says, the induced current and obviously the induced EMF opposes the cause that created it. So cause was actually the changing magnetic flux. The cause was the change in magnetic flux. So actually what Lenz did, Lenz improved or modified the Faraday's law like this. He said the induced EMF is equal to minus of d psi by dt. That is, it is negative of rate of change of magnetic flux linkage. Okay, the minus sign indicates that the EMF induced and then the current induced opposes the change of or rate of change of flux. Okay, so please remember this modification. So now we know the flux is B times A. The flux is simply B times A. So induced EMF in this coil would be, let's say, small e, and it would be minus d phi by dt. As area is constant and the magnetic field is changing with respect to time, we will have minus a and dB by dt. Okay. Let us look at the direction here, because this minus sign is not important numerically. Okay. Just notice the magnitude of induced EMF, and then we will find the direction of induced EMF and the direction of current by simply analyzing the situation by Lenz's law. So as magnetic field is increasing, I'll point my thumb opposite to the magnetic field and the curves of finger will give you direction of induced current. So obviously the induced current is like this, and for this the EMF should be like this. This is induced EMF. Actually, the EMF induced, I have assumed, is similar to a battery, because this battery will make the current to flow in this direction. But according to the perfect theory, the EMF is not induced at a certain location. It is induced in the entire loop. It is induced in the entire loop. It is distributed along the loop in the full length. Okay. So we have E induced. And now we know the direction also. Suppose one wants to know what is the magnitude of induced current in it. The magnitude of induced current. Simply this would be the induced EMF, simply E, divided by resistance of the coil. Because of Ohm's law, the I would be EMF induced divided by R. Okay. Now you know, as I induced is equal to EMF divided by R. Okay. Suppose you are asked, what is average current? What is average current? I average. Obviously the magnitude. Okay. That will be equal to 1 by R times average induced EMF. And as you know, the magnitude of induced EMF is d phi by dt. It would be, the average induced EMF would be delta phi by delta t. The average induced EMF would be delta phi by delta t. Okay. So this is the magnitude of average induced current. Okay. And let us say someone asks you, what is the total charge flown? What is the total charge flown in the loop in that time delta t? Total charge flown in the loop. What is the total charge flown in the loop? So obviously the total charge flown in the loop can be written as the average current multiplied by time. It is simply the definition of total charge flown. It will be average current multiplied by time. So multiply delta t with average current and you get the change of flux, that is phi 2 minus phi 1 divided by R. Or if it is a multi-turn coil, obviously this we will have to multiply by N, or simply you can say the delta Q there would be final flux linkage minus initial flux linkage divided by resistance. Okay. Oh, this is not phi. This is the charge flow. Charge flow. Remember, this is the magnitude of charge flow. And in which direction the charge is flowing, that we already know by analyzing the situation by Lenz's law. We know the direction of induced current. So in the direction of induced current, we can say the positive charge is flowing, or mathematically the positive charge flowing. But you know, actually the negative charge flows in the opposite direction of induced current. So the negative charge will actually flow in opposite direction of the direction of induced current. Okay. So remember these laws, they are quite important, and let's move to our next question. So here we have a long solenoid. We have a solenoid of radius r. This is carrying a time dependent current. So we have a solenoid with a variable current in it, and current is varying with time as this function. Now we have a ring of radius 2r placed coaxially near the middle, and we have to know during the time interval from 0 to 1 second what is the induced EMF in the ring. Okay. Let us think we have a coil like this. The current going in is I. The I is actually I naught. T times 1 minus T is actually multiply T. We have T minus T square. We have T minus T square. And now the radius of solenoid is R. But we have a bigger coil. We have a bigger coil placed coaxially near the middle. And we want to know we want to know about the induced EMF or induced current in the outer coil or the outer ring, in fact. So I think you remember the magnetic field in the region of solenoid is uniform, and that magnetic field is given by B equals mu naught times Ni. As current is changing, the magnetic field is also variable here. So magnetic field is also changing. Okay. Here we have magnetic field 0. Here too we have magnetic field 0. Okay. So can you notice in the outer ring we have flux in the area of solenoid only. So the flux actually crossing the solenoid would also link the outer ring. So flux through outer ring is actually the flux going inside solenoid. And the flux going inside solenoid is B times the area, the cross section area of solenoid, which is B times pi r square. And this is also the flux in the outer ring. Okay. If we want to know the EMF induced in outer ring, the EMF induced would be equal to d phi ring by dt. And d phi by dt would be, B has mu naught n constant, we have pi r square also constant, then we have di by dt. Okay, let's write it again. Actually, I am calculating the magnitude of EMF, right? Magnitude of EMF. So we are not using the minus sign given by Lenz's law. And now I have mu naught n pi r square, and di by dt would be I naught, and differentiate this bracket, you will have 1 minus 2t. So can you notice in the time interval 0 to 1 second, when time is 0.5, if you put the value of time as 0.5, you will have 0.5 times 2, that is 1, and 1 minus 1 as 0. So we have 0 EMF. We have 0 EMF at t equals to 0.5. And before t equals to 0.5, this term is obviously positive, and after t equals to 0.5, this term is negative. So EMF is changing direction. EMF is changing polarity. So if EMF is changing polarity, the current would also reverse its direction. So at 0.5 second, the current would reverse its direction. So B is the correct choice, and obviously when current will reverse its direction, the EMF induced is 0. We have noticed. So B is the correct choice. Okay. Next question. In the next question, they have said a circular coil of radius 10 centimeter is placed in uniform magnetic field with its plane perpendicular to field. So if we have a circular coil and the field, and I'm also taking the plane of coil in this screen and magnetic field perpendicular to the screen. So we have radius of coil as 10 centimeter, the field is almost 3 times 10 to the power minus 5 Tesla, and it is rotated at constant angular speed about an axis along the diameter. Okay, so it is being rotated about an axis along the diameter at a constant angular speed omega. Okay, and it is undergoing half revolution in 0.2 second. We have to find the maximum value of EMF induced in the coil. Okay, so let us redraw this diagram like this. We have a coil. Assume the coil is perpendicular to the screen now, and the area vector would be like this. Assume the magnetic field is perpendicular to the plane of the coil, so magnetic field is like this. Okay. Now if I take a horizontal diameter and I turn this coil with constant angular velocity omega, okay, if the coil will turn, the area vector will also turn, and in time t, the coil will turn by an angle theta, so area vector will also turn by angle theta, and as angular velocity is uniform, it is omega, the theta can be written as omega times t, using the laws of uniform circular motion. The theta is omega t, the angular velocity times t. Okay. So now you know when the coil turns by some angle, the angle between magnetic field and area vector is increasing, is equal to omega times t. So at any time t, if I calculate any time t, the angle between magnetic field and area vector would be omega t, and the flux would be given by magnetic field times area times cos omega t, as flux is B dot A, that is BA cos theta. If I now calculate induced EMF, which is minus d phi by dt, it would be B A, and derivative of cos omega t would be minus omega sin omega t, and the differentiations minus sign would be cancelled by this minus sign, and it would be plus minus sign. Okay, that is why I wrote the perfect equation, not only magnitude. And now we have induced EMF as B A omega sin theta, actually sin not theta, sin omega t. Right. Now they are asking us the maximum value of induced EMF. I think you remember the maximum value of induced EMF will be when sin omega t will be maximum. And the sin omega t, that is sine of any angle, is maximum when that angle is 90. And then the maximum value of sin theta is 1. So maximum EMF induced will be B A omega times 1. Okay. So E max becomes B A omega. Now let's put the values. B is 3 times 10 to the power minus 5. Area is pi times the radius square. Radius is 10 centimeter. So we have radius square as 0.01 meter square. I have converted centimeters into meters. and omega is, as the ring is covering half revolution in, let me see, in 0.2 seconds. So angular velocity would be angular displacement pi divided by 0.2 second. And if now you calculate this, you will notice that it is 10 to the power minus 7, and pi square is approximately 10. So we have 3 by 0.2 times 10 to the power minus 6 Tesla, which is obviously 15 micro Tesla. Okay. So we have EMF induced, maximum EMF induced in microvolt. Okay, it is induced EMF. I did it wrong. The unit is not Tesla, it is volt. So it is microvolt, 15 microvolt, and in microvolt the maximum value of EMF induced is 50. This is the right answer. Next question. Here we have to consider a circular coil of wire carrying constant current I forming a magnetic dipole. So we have a coil having current I and it is forming a magnetic dipole. We have to think about the magnetic flux through an infinite plane that contains the circular coil. So imagine a large, infinitely large plane which contains this coil. Okay, the size can be considered as infinity. And it is given that the flux through this plane, excluding this area, this rings area, is phi 1. So we have flux associated with this surface as phi 1. Okay. And the magnetic flux through the area of the circular coil is phi naught. So the magnetic flux through this area of the ring is phi naught, and we have to think of a relation between phi 1 and phi naught. Okay. Just try to imagine the magnetic field lines created by this coil. I think you remember the magnetic field lines, as the current is this way, the magnetic field at the center is like this, and magnetic field lines are emitted from the area like this. Okay. And total flux associated with this ring is phi naught. If you consider the area vector to be upward, so from the area of the ring we are getting positive flux as magnetic field and area are in the same direction. Okay, and that flux is phi naught. But as you know, these lines go like this and they will cut the infinite plane at some place. They will go downward and they will return back at this point. So these lines cut this infinite plane again at some place. Okay, this too will cut this infinite plane here, this will some here, and this line some here. So all of these lines, they emit like this, they go like this, and they again cut this infinite plane in downward direction, and then from downward direction they come back in the area of the ring. As the size of the plane is infinity, every line which is coming from the area of the ring will be able to cross this plane once more. Okay, and here as the flux is downward, area is again upward, the flux would be negative. So this phi 1 is negative, and as the number of lines which are being emitted are same as number of lines crossing this area downward, obviously the magnitude phi naught and the magnitude phi 1 will be same, but phi naught is positive and phi 1 is negative. So correct option is C, phi 1 is negative of phi naught. Okay, I think you understand this clearly. Let's move to next question. Now here we have a loop. Here we have loop of straight edges and it has 6 corner points the A, B, C and D and E, okay, and F also. If you notice, the A is here at origin, the B is here. If you take X axis as this, the B is here, the C is here, the D is here, the E is here and the F is here. Right? Okay. And if this is the case, now you know the magnetic field in this region is 3I plus 4K. 3I means the magnetic field has one component along X axis, which is 3I, and one, if this is X, this is Y, this is K. So one component of magnetic field along Z direction, which is 4K. And now we have to calculate the flux, the magnetic flux through the loop ABCDEF. Okay. See, as the edge length of every side is 5, this area would be 25 units and this area would too will be 25 units. Okay. So can you see, this component of flux will not, this component of magnetic field actually will not contribute any flux through this area in XY plane, because this flux, this magnetic field is parallel to the area. It will just touch this area, it will not cross this area. But this component of magnetic field 4K will contribute some flux through this area, and if this area is 25, the field is 4, obviously the flux through the bottom area would be 25 times 4, that is 100 Weber. Okay. Now look at this area. As this area is in YZ plane, this magnetic field which is in Z direction will not contribute any flux through this area, as the magnetic field is parallel to the area. It will not cross that area. But this magnetic field, which is equal to 3I, it will cross this flux. It will definitely cross this flux. And if this field crosses this flux, there will be one more flux through the square area in YZ plane, and that will be field times area. The field is 3, the area is 25, so it will be 75 Weber. So the total flux through that area would be the sum of these two, that is 175 Weber. So the correct answer is 175 Weber. Okay. Next question. This time we have a magnetic field of 1000 Gauss is passing perpendicularly through this spatial area. Okay. So we have a magnetic field of, say, inward. So we have an initial magnetic field of 1000 Gauss. Actually, 1 Gauss is equal to 10 to the power minus 4 Tesla. So in SI units, the 1 Gauss is equal to 10 to the power minus 4 Tesla. So we can consider the initial magnetic field B initial is 0.1 Tesla. And after the gap of 5 seconds, the magnetic field becomes 500 Gauss, means half of the initial. So final magnetic field is 0.05 Tesla. Then we have to answer what is the induced EMF in the loop in obviously 5 seconds. So we have to answer what is the average induced EMF. Okay, only magnitude. So as you know, the average induced EMF, the magnitude of average induced EMF would be equal to delta phi by delta t. And as, let us say, area is A, the change of magnetic flux would be A times B2, the final flux, minus A times B1, the initial flux, and divided by delta t. Let us find the area. If you take area of this rectangle, that would be 16 times 4. 16 times 4, which is 64. But we have to subtract the two triangles forming here, and the area of each triangle is 4 centimeter square, because the triangle's area is base times height times half. So the area of each triangle is 4 centimeter square, area of two triangle is 8 centimeter square. So the total area of rectangle 64 minus 8 is 56 centimeter squares. So the area is 56 centimeter square. Convert this into meter square. So this will be having area as 56 times 10 to the power minus 4. Then we have B2 minus B1, that is change of magnetic field, and the change of magnetic field would be, let's say magnitude of change, the change of magnetic field would be minus 0. But as we are calculating magnitude only, I'm ignoring the minus sign. So the change of magnetic field would be 0.05 divided by 5. Okay, and you can see the answer is 56 times 10 to the power minus 6 volt. So obviously 56 microvolt is the right choice of option. Next question. Here again we have the magnetic flux through the loop, and the magnetic flux is increasing according to the relation 10t square plus 20t, where phi b is actually in milliweber. So this is in milliweber, remember, and time is in second. We have to answer the magnitude of current to the resistance R at 5 seconds. Okay. So as you know, the induced current is equal to induced EMF divided by resistance. So let us find induced EMF, and what is induced EMF? It is equal to d phi by dt. It is equal to minus d phi by dt, but we have to calculate just magnitude, so it is simply d phi by dt. So just differentiate phi and you will have E as 20t plus 20 divided by R. Okay, and since it is in milliweber, the flux is in milliweber, we will have current in milliampere as R is in ohms. Okay, so at 5 seconds I induced at t equals to 5 seconds will be found if we put the time as 5 seconds. So put time as 5 seconds times 20 is 100 plus 20 is 120 divided by R as 2 ohm milliampere. So we'll be having 60 milliampere. So current is 60 milliampere. That is the right answer. So that's all about the Faraday's laws and the changing magnetic field. The next is motional EMF. And why it is called motional EMF? It is also a kind of induced EMF, but it is generated when some conductors move in magnetic field. We have magnetic field, usually stationary, usually constant in these cases, and when a conductor moves in magnetic field, we observe a potential difference across the ends of the conductor, and that potential difference, as it is because of motion of the conductor, is called motional EMF. Okay, so let us first take a very usual, very popular example of motional EMF, where we have a magnetic field. Let us say magnetic field is pointing inward, perpendicular to the screen. We have a conductor AB. And it is moving like this. The length of the conductor is, say, L. The speciality about this case is all three terms, the velocity, the magnetic field, and the length of the conductor, all three are mutually perpendicular. Can you see? The B and L are perpendicular. B is inward, L is like this. The L and V is perpendicular, and the V and B also perpendicular. All three are mutually perpendicular. And if all three are mutually perpendicular, this is the most important case as far as the questions are concerned. Okay, so we will take first this case. As this conductor moves in magnetic field lines are cut by the conductor. what happens with this? The free electrons whose average velocity is zero, they can be considered on an average at rest. They all start moving like this. All electrons start moving like this. And because of the motion of electrons, they experience a force in magnetic field. As V cross B, can you see the V cross B is upward, the electrons will experience a force downward. This is magnetic force downward. And because of this, the lower end will be negative because electrons are moving downward, and the upper end will have a relatively positive charge because electrons have shifted downward. And this will create some induced electric field inside this. E induced, because from positive charge to negative charge there is always some field, and because of this field some potential is developed in this region. Okay, the potential that is developed here is called motional EMF, and in this case the potential difference is given by BVL. Simply multiply B, V and L all in SI units and you will get voltage, the motional EMF across this wire in volts. Okay, always remember, can you see the V cross B is pointing upward towards A and end A is positive. So always remember the end of conductor, the end towards V cross B. V cross B is again a vector. So this vector when points towards some end, that end is positive actually. The end towards V cross B points is positive. Always remember the end towards V cross B points is positive. This conductor can be assumed as if it is a battery. It is similar to a battery with positive end towards A, and the voltage V of the battery, the EMF of the battery can be considered as BVL. So if we have in a circuit a moving rod like this in magnetic field, that rod can be replaced by a battery of EMF BVL with positive ends towards the direction of V cross B. Okay, remember this point. In general, when there are different angles between VB and L, let's say velocity is variable, let's say magnetic field is variable at different points, then in general case, the motional EMF is given by integral of V cross B vector dot dl vector, and this integration is done over all dl such that every element of the conductor can be considered. Okay, so this is the net voltage, net potential difference developed across the conductor placed in non-uniform magnetic field, or if the conductor has a irregular shape, you should use this one. Okay, so that is the general case. Okay, and here we see a very interesting point. Suppose the velocity and magnetic field are parallel with each other or anti-parallel with each other. If velocity and magnetic field are in one line, the V cross B would be 0, so voltage developed, the motional EMF would be 0. So if V is parallel with B, the motional EMF is 0. Let's check the case when V is parallel with L, when velocity is parallel with L. Remember, as V cross B vector is perpendicular to V and B both. So remember, if V cross B, this vector in the bracket is perpendicular to V, it is also perpendicular to L. as V and L are parallel. So if this vector is perpendicular to L, it will be perpendicular to DL, all DL. And if it is perpendicular to DL, all dot product will be 0. So here also we have voltage 0. Let's check the third case. If B is parallel to L. If B is parallel to L, obviously this vector will be perpendicular to B. So it will be perpendicular to GL also. So all these dot product will be 0. And again we have potential difference 0. So always remember, if any two among the three B, V and L are parallel, the potential difference, the motional EMF will be 0. If any three among B, V and L are parallel, the motional EMF is 0. If all three are mutually perpendicular, the motional EMF is BVL. And if you see any other case, use this general law. Let us see some problem based on this. So here we have a square loop of side 20 centimeter. We have a square loop of side 20 centimeter and resistance 1 ohm. We have resistance of this loop as 1 ohm. And it is moved towards right with a constant speed V naught. And the right arm of the loop is in the uniform magnetic field E. So do not confuse only the right arm. They have said only the right arm of the loop is in magnetic field. So if right arm is in magnetic field, the magnetic field is pointing inward. Can you see the magnetic field is pointing inward? Okay. The length is perpendicular to magnetic field. And velocity is perpendicular to both magnetic field and length. So we have a case of all three BVL perpendicular with this rod. So here in this rod, we will see some motional EMF. So here we will have some voltage V, and the voltage V would be equal to BVL, magnetic field, velocity and length. If some portion of these rods come into magnetic field, there will be no potential difference across any part of these rods, because for these rods velocity and length are parallel. Can you see, as the loop is moving towards right, the velocity is like this. So for this rod we have velocity and length parallel, for this rod we have velocity and length parallel. So no EMF induced in these rods, and these rods are clearly outside the magnetic field. So only in this rod we see some potential difference. So let us find potential difference. Potential difference is simply BVL. B is 5 Tesla. Velocity is velocity we have to know. Velocity we have to know, and the length is 20 centimeter. Okay. So the V will be equal to 5 V naught and L as 0.2. So we have 5 times 0.2 as 1. So the voltage developed is equal to numerically the velocity V naught. Okay, the velocity. And as the resistance of this loop is 1 ohm, and here we have 4 ohm in series, 8 ohm. We have 4 ohm in series, 8 ohm, and 8 ohm in parallel, it becomes 4 ohm. So 4 ohm and 1 ohm. There is a total of 5 ohm resistance, and if I divide voltage, which is equal to V naught, the voltage is equal to V naught divided by 5 ohm, it gives us current. And the current here is 2 milliampere. Current here is 2 milliampere, that is 2 times 10 to the power minus 3 milliampere. So we get velocity as 10 millimeter per second. 10 millimeter per second. So we can write 10 to the power minus 2 meters per second, and that becomes actually 1 centimeter per second. So correct choice is B. In this question we have a square frame of side 10 centimeter. We have a square frame of side 10 centimeter, and it is placed close to a straight wire, a long straight wire carrying upward current as 1 ampere. Okay, and they both are in same plane. They say the loop is moving towards right with some velocity V. The loop is moving towards right with some velocity v, and they are asking us the EMF induced in the EMF induced at the time the left arm, EMF induced in the loop, the EMF induced in the loop at the time the left arm of the frame is at a distance 10 centimeter from the wire. So we have to answer the net EMF induced in the loop when this side, the left arm, is at a distance x from the wire. Okay. As you know, the field of the wire is different at different places. As you go away, the field changes. So field is variable here. But as the field does not change if you move parallel to wire, it changes when you move away from the wire. So at the place of left arm, we have constant magnetic field. Let this magnetic field is B1. So I can say this entire edge is in uniform magnetic field B1, and this entire edge is in uniform magnetic field B2. And these are the two wires across which some motional EMF will induce, because for these we have B inward, V rightward, and L vertical. All three B, V, L perpendicular. For these two, there is no EMF induced, as we have length and velocity in same direction. So these two wires only have motional EMF. Okay. Let us see how much. As the V cross B is upward, we will have motional EMF in this wire as this. Let's say V1, positive upward. And in this wire also we have V2, positive upward. Okay. As magnetic field of this wire at a farther distance is less, so B2 will be less, and if B2 is less, V2 will be small. So if V2 is smaller, the net EMF in this loop would be V1 minus V2. Okay, V1 minus V2. So I can write net EMF as V1 minus V2. Okay. Let us write V net, V1 as B1 velocity and length minus B2 velocity and length. Length and velocity are common for both. The field are different at the two wires. So I can take VL common. So if we have B1 minus B2 times velocity times L. Let us put all the values. As you know, B1, B2, the formula is mu naught I divided by 2 pi x. So I can place, in the place of B1, I can place x, and x is 0.1 in meters, right? And can you see the other arm is 10 plus 10, 20 centimeters from the wire. So we have the second length has 0.2. The velocity is, the velocity is 10 meter per second, and the length is 10 centimeter. So we have velocity as 10 meter per second and length is 10 centimeter, that is 0.1 meter. Okay, let us multiply these. So we have 1 here and we have 10 minus 5, that is 10 minus 5 is 5. So we have mu naught I divided by 2 pi times 5 here, right? I is 1 ampere, and I think you remember mu naught by 2 pi. Mu naught by 2 pi is actually 2 times 10 to the power minus 7. Okay, 2 times 10 to the power minus 7 times 5. So we have 10 to the power minus 6 as an answer as volt. So answer is 1 microvolt. It is the net EMF induced in that loop, and answer is B, 1 microvolt. Next question, a very interesting question. Here we have a copper rod of mass m and it is sliding under gravity on two parallel rails. So we have this length of this rod of length L, actually mass m and obviously the length L, and it is sliding on these two inclined rails. Okay, I can draw the side view of this rails, and the rails are inclined at an angle theta with horizontal, and the cross section of rod would look like this. Okay. If the rod is moving with some velocity and it is placed in magnetic field, some EMF will be induced. Some EMF will be induced, and let us see, the velocity will be downward. Okay, the field is upward, so positive end will be inward. So this like EMF is induced here, V, and that EMF would be BVL. So we have EMF as B, velocity, and L. If this is the EMF, in this loop a current will flow, a current will flow, and the current would be EMF divided by resistance. This is the value of current. And if this is the value of current, this will become a current carrying wire. This will become a current carrying wire, okay, in magnetic field. And I think you remember, on current carrying wires in magnetic field, they all experience a magnetic force. All other wires will too experience magnetic force. The rails and the resistance will too experience a magnetic force, but they are fixed. Only this rod is movable. So let us see, if the current is like this, as suggested by direction of EMF, we have current inward. Okay, we have current inward. And if we have current inward, we have current inward and magnetic field like this. The direction of magnetic force as it is in the direction of I cross B. So I cross B is upward. So on this wire, a magnetic force will try to oppose the downward motion, and the magnetic force becomes IBL. Remember, the magnetic force on current carrying wire is IBL. So it is I, then B and L. It is the magnetic force that is opposing the downward motion. Who is supporting the downward motion? The mg sine theta component. The mg sine theta component is bringing the rod downward. So we have to answer the terminal speed. I think you remember, when speed is terminal, the net acceleration of the body is 0. And if net acceleration of the body is 0, the net force on it is 0. So as on the rod, an upward force Fm acts, and in downward direction we have mg sine theta. These two forces must be equal when velocity is terminal. So we get the value of terminal velocity as mg r sine theta divided by b square upon l square. So the correct answer is B. The Gauss's law of magnetism. Okay, it is a very small law, but it tells a lot about magnetism. Okay, so suppose we are calculating the magnetic flux through a closed surface. Suppose this has a closed surface. Okay, and it is placed in magnetic field created by magnets or created by currents, anything. So closed loop magnetic flux will be written as B dot dA, and this is the symbol for closed integration. If we calculated this, suppose imagine a line is crossing this surface. As you know, magnetic field lines are always closed loop. The line cannot terminate on any point outside. The line has to come back to this point, so it has to penetrate this loop again and come back to the starting point, because the magnetic field lines are always closed loop. No line can cross the loop and just terminate on any other point. It has to come back to the starting point. And that is why, suppose it is going like this, and it has to come back to the starting point. So any line that would cross a closed loop coming outward will also cross the loop again going inward. So you see, if n lines are crossing the loop, crossing the closed surface outward, they will again cross the surface inward sometime. Therefore, you can say the outward flux and the inward flux will always be equal. And if outward flux and inward flux are always equal because the magnetic field lines are closed loop. Therefore, you can say the net flux through that closed surface is always zero. Due to the fact that magnetic field lines are always closed loop. It also says one very important line. Let me tell you. Suppose you have a magnet. If you have a tiniest magnet, then also in that magnet too, you will have two poles, one north pole, one south pole. Suppose try to imagine you have a magnet like this. North pole, south pole. And you argue with me that if I take a surface like this, that encloses only north pole, will there be any non-zero flux with this surface? I would say no, because the lines which are coming from north pole, they go and they come back in the magnet from south pole, and then inside the magnet they travel like this and they again come back to north pole. So these lines too come to north pole again and the net flux is still zero. But suppose, try to imagine, we have a special magnet that has only north pole. If you have a special magnet that has only north pole, means only a single pole, means only a monopole, then if you enclose this with a Gaussian surface, obviously it would have some flux associated with it. But since this type of pole do not exist, whenever we find a magnet, we find this with two poles, north pole and south pole. So this law also says that single magnetic poles means monopoles do not exist. Monopoles do not exist. Okay. So always remember this. The magnetic flux through a closed surface is always zero. Okay. So motional EMF is not over yet. We have considered a case when the rod was in translation, when the rod was moving in translatory motion. Suppose we have a rod that is rotating. Suppose we have a rod like this of length L. It is placed in magnetic field. The plane of motion of the rod is perpendicular to magnetic field. The magnetic field is B and the rod is rotating like this. The angular velocity is omega. The angular velocity is omega. So this rod also has some motional EMF developed across its ends, and that motional EMF is equal to B omega L square by 2. Remember, if a rod is rotating about an axis which passes through one of its ends, see, the axis is passing through this end. So if axis passing through one of its ends and angular velocity and magnetic field are in same line. See, can you see? The angular velocity is inward, the magnetic field is inward. Okay. Then we have, this is not B, it is motional EMF or V. And the voltage, the motional EMF is equal to B omega L square by 2. Remember this point. The motional EMF in case of rotating rod, rotating about one of its ends, is B omega L square by 2, where B is magnetic field, omega is angular velocity, and L is the length. Okay. Also remember, if you see the velocity of this point is towards left, the magnetic field is inward. So let me flip my hand like this. Velocity cross B. My thumb is pointing downward. So this end should be positive because here we have V cross B. The V cross B is downward. So we have positive end this and the central end is negative. So this rod can be replaced as a battery like this, if this is the rotational axis. If we have magnetic field inward, but the rod rotating like this, anti-clockwise, you would see the velocity towards right, the magnetic field inward, the V cross B will be upward, and this end would be positive, this end would be negative. So that will help you decide the direction of induced EMF. Okay. So always remember, if a rod rotates with some angular velocity about one of its ends, the motional EMF across it will be B omega L square by 2, where B is its magnetic field. So this is a very important question. Here we have a metallic rod. Always remember, the EMF can be induced in metallic rods only, because in metallic rods we have free electrons. In metallic rods, electrons can shift and EMF is induced. Okay. So if a metallic rod of length L is tied to a string of length 2L, so we have rod of length L and we have a rod of length, string of length 2L, and this is rotating about this with angular speed omega. Okay. So the rotation of rod is the plane of table, and magnetic field is upward. So obviously the rotational plane is perpendicular to the magnetic field, everything is okay, and we have to answer the EMF induced across the ends of the rod. The difference between this situation and this situation is that in this rod we had axis at one of its ends, but here the axis is here and ends are here. So the axis is not passing through any of the ends of the rod. Okay. So what we can do, we can imagine a rod of length 3L and we can find the EMF induced in this rod of length 3L. That we can find because of using this formula, because if we take the rod's length as 3L, the end is touching the axis is at the end, but that would be a wrong solution. But what I'll do, I'll cut a part of it of length 2L and I'll remove the potential difference or the EMF induced in this part from the entire part. Then I will get the EMF induced in this part. Obviously, if I take or calculate the EMF induced in this entire rod of length 3L and I remove the EMF induced of part 2L, I'll get the right answer. Okay. So the net answer is the EMF induced in the rod is, find the EMF induced in the rod if it had length 3L. So it would be B omega 3L square by 2 and minus EMF induced in the rod of length 2L, because it is not present here. So minus B omega 2L square by 2, and you will get B omega 9L square minus 4L, 5B omega L square by 2. So the correct answer is D. So here in this question we are given that we have a coil of some specific resistance and magnetic flux in the coil is changing, and because of that some induced current is flowing, and we are given that the current is changing with time as according to this graph, and we have to find what is the net change of magnetic flux in the coil. As you know, the induced current magnitude, let's say I, it is equal to induced EMF divided by resistance R. So I can write I equals to, as E induced is given by rate of change of flux. Actually we are talking about only magnitude, so the sign is not important. So I can write 1 by R and d phi by dt. If you bring this dt on the left and integrate this result, you will have I dt equals 1 by R d phi, and integrate this. As the limits of time are from 0 to 0.5 and we are asked the net change of flux, so this can be written as Okay, I think you remember this represents actually the area under the curve, or also the charge flown during this time limit. So it is actually the area under the curve. So I can write area under the curve equals the change of flux divided by resistance. Okay, so it gives you the change of flux as area multiplied by resistance. As the resistance is 100 ohm and area, let's calculate the area. As area of a triangle is half times base multiplied by height, so the area would be half times base. Base is actually 0.5, so it will be 1 by 2, and the height, which is current, maximum current, which is 10 ampere. So you solve it, you get 1000 by 4, and that is 250 in SI units, which is Weber. Okay, so this is the change of flux in the coil. Now we have to move to next very important concept, and that is of induced electric field. I'm sure you must have heard about electric fields, and the source of electric field is actually electric charge. That is our common conception. But you'll be surprised to hear that we have another source of electric field. We have one more source of electric field, and that is the changing magnetic field. Isn't this amazing? Without having charge, you can create electric field. Just put a magnetic field in a region and change it with time, and if magnetic field is changing with time, we observe that an electric field is produced. The special thing about this electric field is it is not like the electric field produced by stationary charges. It is actually in nature non-conservative. Okay, so let us understand this observation. Okay, so the observation is whenever magnetic field through a region changes with time, it changes with time, a non-conservative closed loop electric field is induced. It is observed actually. Okay, it is an observed fact. Okay, so a closed loop electric field is induced, which extends up to infinity. As the point charge fields also extends up to infinity, this field also extends up to infinity. So the main points are, when magnetic field in a region changes with time, a non-conservative field is produced, and this non-conservative field is closed loop type. Okay, as I think you remember, the electric field produced by charges never form closed loop, but the difference with field created by changing magnetic field has a special feature that it forms closed loops. Its electric field lines will be closed loops. Okay, so remember this fact, and let's now understand this observation a little more. Okay, if you want to know the direction of electric field, remember the direction of electric field will be given by Lenz's law. Okay, and we find the direction of electric field the same way we used to find direction of induced current. Okay, so whenever you want to find direction of induced electric field, always try to apply Lenz's law in same way we used to apply this for finding direction of induced current. Okay, so we are going to understand a very special observation, okay, of induced electric field. Suppose we have a cylindrical region whose cross section is shown, and in this cylindrical region of radius r, we have a magnetic field. The magnetic field is uniform in space. It is same at all points, but with time it is changing. And let's say the rate of change of magnetic field, is dB by dt. I can also call it alpha. So dB by dt is the rate at which the magnetic field is changing. This rate may be a constant, it may be a variable also, but right now I'm assuming the dB by dt as alpha. Okay, And what we observed, remember, it is an observed fact. It is an observed fact. So we are just interpreting the observation that we observe. Okay. So what we observe is, when this magnetic field changes with time, an induced electric field is generated here. That electric field is non-conservative, and that electric field is closed path, enclosed path. Okay. So what we get here a circular electric field like this, and this electric field, this induced electric field, extends up to infinity. Means we also get electric field in the region of changing magnetic field. We also get electric field in the outside region of changing magnetic field. Okay. So if we wish to find the direction of electric field, what we will do? We will apply Lenz's law. Okay. And how Lenz's law is applied? Okay. Suppose the magnetic field here is increasing. When magnetic field here is increasing, we will put our thumb of right hand in opposite direction of magnetic field. Remember, we'll put our thumb in opposite direction of magnetic field, and curls of fingers, they used to give us direction of induced current. Here they will give us the direction of induced electric fields. So as the curls of fingers are anti-clockwise, the induced electric field would be anti-clockwise. Okay. If we are interested in finding the magnitude of this electric field, let me write the magnitude of electric field. But remember, we have two formulas. One is valid in the region of magnetic field, and one is valid outside the region of magnetic field. Suppose we wish to find the magnitude of electric field at a distance r from center of symmetry. This is the center of symmetry, and we wish to find electric field at a distance r from it. So when r is less than the radius of the region of magnetic field, means r is less than r, we are inside magnetic field. And what we observe, inside magnetic field, the electric field is given by r by 2 dB by dt. Here we get magnitude only, and direction will be found from Lenz's law, as I explained. And if you are wishing to find electric field, induced electric field outside the region of magnetic field, the R would be more than capital R. And here we find the electric field as R square divided by 2R, where small r is the distance from center and capital R is the radius of that cylindrical region, multiplied by dB by dt. So can you see, within the magnetic fields region, the electric field is proportional to R. At the center of the symmetry, we have zero electric field, and as we are moving away from center, the magnitude of electric field increases. Okay. And when we move outside the region of magnetic field, the electric field starts decreasing as 1 over R. It is proportional to, can you see, the E here is proportional to 1 over R. So maximum electric field we get on the boundary of magnetic field here, on the boundary of magnetic field. So initially the induced electric field is linear, and then it decays from maximum value, it decays hyperbolically. Okay. So these are the two formulae. You remember them well, and let us understand the pattern of field. Okay. So I have taken the white boundary as the boundary of magnetic field. We have magnetic field within the circular boundary drawn by a white circle. We have magnetic field here. If this magnetic field is changing, and let us say magnetic field is increasing, B is increasing, magnetic field is increasing. When magnetic field is increasing, there will be circular electric field lines. These are circular electric field lines. Remember, they are not produced by point charges or stationary charges, they are produced by variable electric field, variable time varying electric field. It extends up to infinity. Remember, this electric field shown by the green curves is non-conservative. It forms closed loops. As the symmetry is circular, the shape of electric field lines is also concentric circles. And if you wish to find the direction, we use Lenz's law. If B is increasing, point your thumb outside, opposite to the direction of magnetic field, and curls of fingers give you the direction of induced electric field, and the magnitude is given by this result. Within the boundary of magnetic field, electric field is R by 2 dB by dt. Outside the boundary of magnetic field, we have electric field as this value. This depends upon the rate of change of magnetic field, as you can see. So if the magnetic field changes at faster pace, the electric field is stronger, and if it changes slowly, the electric field is weaker. Okay. So remember, the electric field here is not depending upon how big is the magnetic field is. It depends upon how fast the magnetic field changes. So here we have a question related to this, and it asks us that this figure shows a circular area of radius r. This figure shows a circular area of radius r, and in this area we have a uniform magnetic field. Uniform means the magnetic field is not changing at different locations. It is uniform with respect to space, but it is changing with respect to time. With time it is changing. Okay. And they have asked us what is the variation of electric field as we move from center of this region and move away. Okay. So as we remember, the electric field inside the region of magnetic field is equal to R by 2 B dash. B dash here represents the rate of change of magnetic field, or simply d by dt. B dash is dB by dt. So inside we have electric field as R by 2 B dash, and outside we have electric field R square by 2R B dash. As you can see, within the range, within the radius capital R, we have a linearly varying electric field, and at center the electric field is 0. So we should have a linear relationship like this. We have three options with linear relationships up to the radius r. But after that we can see the electric field decays hyperbolically, because electric field is proportional to 1 by r, and that curve is supported here in option D. As option A has also a similar shape as D, so A2 will be your correct choice. So according to the data given, we have two correct options, A and D. Okay. So now let's move to the next concept of self-induction. Okay. Let us understand the self-induction. What is self-induction? Suppose we have a coil. And there is some current flowing in the coil I. Because of this current, a magnetic field also develops here, like this. And these magnetic field lines cross the cross-section area of the coil. So I can say the flux is linking this coil. So the flux is linking this coil. So actually here we have the flux linked with coil due to its own current. So whenever there is a flux through a coil due to its own current, this flux is called self-flux of the coil. This flux is called self-flux of the coil, remember. And whenever the self-flux means the flux because of its own current changes with time, there will be an induced EMF in the coil according to electromagnetic induction principle. So if this current changes or any other region, if the flux is changing with time, there will be induced EMF in the coil. Okay, and that induced EMF is called self-induced EMF. Self-induced EMF, and this phenomenon is called self-induction. Remember, this phenomenon is called self-induction. You can always say, let us say the self-flux is phi. Obviously the flux will depend upon the current, because this current produced magnetic field. The magnetic field intensity depends upon current, and on magnetic field the flux depends. So we can say the flux is proportional to current. The self flux is proportional to the current flowing in the coil. Okay. If I add a constant of proportionality, a constant L here, the phi becomes L times I, where L is a constant of proportionality. Remember, L is a constant of proportionality. What is L? L is actually a constant of proportionality, and L depends upon shape and size of the coil. Remember, shape and size of the coil, and also on the medium in the coil. Okay, or in fact on the permeability of the medium in the coil. The name given to the L is inductance. L is called inductance of the coil, and the coil whose inductance is L, that coil is called an inductor. Okay, an inductor. So we can say the coil as inductor, and L is its self-induction property. Okay, the unit for the inductor is obviously the Weber per ampere. Can you see L is equal to phi upon I? The unit of phi is Weber, the unit of I is ampere, so it is Weber per ampere, but it is popularly known as Henry. Okay, so Henry or Weber per ampere is SI unit for flux, self-induction. So always remember, if a coil has current I and its self-inductance, that is L, is given, you have the self-flux as L times I. This is the self-flux linked with that coil. Okay, and when this self-flux changes with time, what happens? As we have a coil, say the current being sent in this coil is changing with time. If current is changing, the flux equals to Li will also change. And if flux changes with time, an EMF is induced. Remember, that is the principle of electromagnetic induction. So we have induced EMF equals to minus d phi by dt, and as you can place phi as L times I, as L is a constant, you can take it outside and you are left with minus L di by dt. So always remember, E induced equals to minus L di by dt. So what's the summary? The central idea is, whenever current in a coil changes with time, there is an induced EMF developed in the coil, and according to Lenz's law, this induced EMF tries to oppose the change causing it. Means if the current is increasing, it will try to decrease the current, and if current is decreasing, it will try to increase the current. Always remember, it always opposes the it never opposes the current, it only opposes the change of current. So if current tries to decrease, it tries to increase the current. If current is increasing, it tries to decrease the current. Okay, so direction of EMF will be found from Lenz's law. Let us understand a little bit more about this. So whenever we want to find the direction of E induced, always remember the fact that it will be given by Lenz's law. So usually in circuits we are given the inductors, and obviously by looking at the circuit we can find the direction of current. So suppose between A and B we have an inductor. And if we move from A to B, we can write KVL here. And always remember, when we move in the direction of current in an inductor, the potential is believed to be dropped by L di by dt. The potential is believed to be dropped by L di by dt. So if you move from A to B, just write VA as potential of A, and as we are moving along the direction of current, potential drops by L di by dt. So I'll write minus L di by dt, and as we reached point B, I'll write potential at B. This is the open loop KVL across the inductor written here. But remember, this di by dt may have a negative sign or a positive sign. So remember, whenever you see the current is increasing, if current is increasing, di by dt will be positive, and if di by dt is positive, give it a positive sign. But in some case, if in some case you notice that current decreases with time, so if current decreases with time, always give di by dt a negative sign, and that will give you perfect answers. Okay. Suppose we have this question, and in this question they ask us what is VA minus VB, and if the current whose direction is shown is 2 ampere and current is decreasing at 5 ampere per second. Current is decreasing at 5 ampere per second. So let us start writing open loop KVL from A to B. We will start from A. I'll write VA and C. We are moving towards B. So we are crossing an inductor in the direction of current. So I'll write minus L di by dt, because in the direction of current, potential decreases. Okay. Then we have a battery. Battery's polarities are like this. So if we are moving from left to right, potential decreases by 3 volt. Okay. And in the direction, in the resistance also, we have current like this, and in the direction of current in resistance also, we have a drop of potential, and potential in resistance drops by I times the resistance R. Now we reached point B, so I'll write VB. Okay, now let's put the values. We have VA minus L, L is 2 Henry, di by dt. Did you notice that current is decreasing at a rate of 5 ampere per second? So if it is decreasing at a rate of 5 ampere per second, the di by dt will be minus 5, as we have seen a decrease in current, right? And then we have 3 and minus I is 2 ampere and R is 5 ohm equals VB. Let us calculate. We have VA plus 10 minus 3 minus 10. Okay, so we have minus 3 equals VB, and if you bring VB here and minus 3 on the right hand side, you get VA minus VB as 3 volt. So this is your right answer. So remember, always in the direction of current in inductor as well as resistance, if you move in the direction of current, always write, always assume that potential is decreasing, give it a minus sign. But remember, if current increases, give di by dt a positive sign, and if current is decreasing, if the current is decreasing and its rate of decrease is known to you, put the numerical value with a negative sign, and that will give you the correct answer. Okay, so that is a little bit about self-inductance. As I said, this property of self-inductance is related to coils. But obviously, if we have a single turn coil or 2-turn coil or a very low number of turns coil, this effect is not very strong. But if you have a multi-turn coil like we have in solenoids, this effect plays a major role. Okay, so suppose we have a almost ideal solenoid whose length is very large as compared to its cross section. The length is L and the radius is R, and let us say the number of turns are N per unit length, means per meter. Okay, N 10 turns per meter. Let me write N turns per meter. Okay, and we send a current I in the solenoid. As we send the current I, the magnetic field will develop in the solenoid, and as magnetic field develops in solenoid, A flux also develops in solenoid. So as you know, the magnetic field in the solenoid is approximately mu naught n times I. And if this is the magnetic field and we want to know the flux associated with one turn, with a single turn, so flux associated with one turn will be given by B times area of that turn, and area of that turn is obviously pi r square because the radius of solenoid is r. But this is the flux linked with only one turn. If we are wishing to find the net flux linkage or the flux linked with entire solenoid, I'll say the flux because of linking of flux with all the turns, or flux linked with solenoid, and since this flux is because of its own current, I can call it self flux of solenoid. Self flux of solenoid, and that will be flux linked with one turn multiplied by total number of turns here. So let us write the flux by one turn as B into pi times r square, and as the number of turns per unit length is n, so number of turns in the L length would be n times L, obviously. And let's put the value of B here. So we have phi as mu naught n I pi r square, that is cross section area, L, and we have one more n, so we do n square. So this is the cell flux, and can you see the cell flux is depending upon the current? It is depending upon the current. So you can write a famous relation, that is phi equals to L times I. And if you compare these two results, you will notice that self-inductance of this coil is given by mu naught n square times cross-section area times length, and cross-section area times length is actually the volume bound by the solenoid. So actually you always remember the self-inductance of solenoid is mu naught times n square, where n is the number of turns per unit length, times volume. And if someone asks you what is the self-inductance per unit volume, it will be simply mu naught n square. Okay. So remember this result. Let's move. Obviously, we can use inductors in circuits. And if we have multiple inductors in circuit and inductors are connected like this, the first inductor, the second inductor, like this, L1, L2. So they will be called in series. And if inductors are found in series, the net inductance, the two or multiple inductors can be replaced by a single equivalent inductor, and that equivalent inductance is given by the sum L1 plus L2 plus L3, etc. So the operations of inductance in combination are similar to those of as resistance. Okay. Also, when inductors are in parallel, you can combine multiple inductors as you have combined multiple resistance in parallel, and the net inductance is given by 1 by L equals 1 by L1 plus 1 by L2 plus 1 by L3, etc. So remember, the operation here is same as that of resistance. Okay. Now we will talk about the very important LR circuit, which is one loop LR circuit, where we have one inductor, one resistor and one battery. Initially there is no current, and when we close the switch at t equals to 0, we are assuming that initially at t equals to 0, we have closed the switch. Now the current will begin flowing. So let us assume at time t, after the t seconds of beginning of the circuit, let the current in the circuit is I. And now we will write KVL equation for the loop. Let's start from here. Write KVL. As we move up, the potential increases as we are going from negative to positive terminal of the battery, we will write V. Then we go from here, and can you see in the direction of current, as potential decreases in R, we will write minus I times R, and also we are moving in the direction of current in inductor, we will write minus I minus L di by dt equals to 0, because we reached the original point. So this we can write as L di by dt equals V minus I times R, and let us write di divided by V minus IR equals to dt divided by L. Now if you integrate this equation, as the current was 0 when time was 0, this was the main assumption, that initially there was no current in it, and let us assume at time t the current is I. If you integrate this result under these limit, you will find the current variation with time as V upon R, and inside bracket we will be having 1 minus e to the power minus RT by L. If you place t equals to infinity here, e to the power minus infinity is 0, means after a very long time from the beginning, the current in the circuit is simply V by R. The current in the circuit is simply V upon R, and L divided by R is called time constant of the circuit. After one time constant, the current reaches 63% of its maximum value, which is V upon R, and if we plot this current versus time, we get variation like this, and this is the maximum current, and after one time constant, that is L by R, we get current as 63%, that is 0.63 times of V by R. If you wish to find potential difference across resistance or inductance, so VR is given by I times R. Simply multiply this current by R, you get the potential difference across resistance, and the VL is given by L di by dt. So simply differentiate this result and multiply that result by L. It will give you the potential difference across inductor. So remember these results. This is a very important circuit of the chapter, and now let us understand the power analysis for the same circuit. If you notice the KVL I just wrote, it was V minus IR minus L di by dt equals to 0. If we multiply this equation by current and transfer the negative terms on the right hand side, we will get V times I equals I square R minus L I di by dt, plus L di by dt. If you notice, this is the rate at which power is being delivered by the battery. So this is power by battery. What is I square R? I square R is the rate of dissipation of heat in resistance. Rate of heat dissipation in resistance. And in inductor, the energy is being stored. So this represents the rate of energy being stored in inductor. Rate of energy being stored in inductor. Okay, we understand these two terms very well. Let us interpret this result a little bit more. So, the rate of energy being stored in inductor is as L times I di by dt. Transfers this dt on the left hand side, you will get p dt equals to Li di. Let us assume again, if at t equals to 0, the current was 0, and at time t, the current is I, this gives us the power times dt. The integral p dt gives you the energy being stored. Okay, because this is the rate of energy being stored, and the rate times dt will give you total energy stored in inductor. So this is energy stored in inductor, and this integration would result L I square by 2. So if at any moment the current in inductor is I, the current in inductor is I, the total energy stored in that inductor would be Li square by 2. Li square by 2. Remember this result. We also learn the behavior of inductor in the circuit. As you know, when you switch on this switch, the current as a function of time is given by I equals V by R and 1 minus e to the power minus RT by L. Let us understand this behavior initially and after a long time, because in between those limits, at any moment of time, you can find current from this function. So what is current in the beginning? Current at t equals to 0. Current at t equals to 0. You put t equals to 0 here, you get e to the power 0, and e to the power 0 is 1. So 1 minus 1 is 0. So the initial current is 0. If initial current is 0, it means the circuit is on, but still we have 0 current initially at the initial moment. Means this inductor behaves as an open switch. Inductor behaves as an open switch. Remember, initially inductor L acts as an open switch, because in those open switch conditions only we have 0 current in the circuit. So inductor behaves as an open switch. Remember this point. And after a long time, when t is tending to infinity, when everything in the circuit got settled, the steady state has arrived. Now let us see what is current. The current now is, put t equals to infinity here, you get e to the power minus infinity. And as t to the power minus infinity is 0, 1 minus 0 is 1. So I is simply V by R. And if I is V by R, it seems like there is no inductor in the circuit. We have simply a battery and one resistance. And the current is V by R. So inductor is not doing nothing. It is just acting as a straight path, a resistance-less path. So now, after a very long time, inductor acts as a conducting wire, a resistance-less conducting wire. Resistance-less conducting wire. Understanding this behavior is very important, because you will be asked many questions about LR circuits, and they will ask you only about initial and final conditions. So if they ask you just in initial conditions or just in final conditions, just assume initially inductor as an open switch and just write the result according to the circuit. And if they ask you what is the final current or what is the final behavior of the circuit, just assume inductor as a resistance-less wire and solve by using KVL or something. Okay. So this was the behavior of inductor in LR circuits. Now it's time to solve few problems based on this. So here in this question it is said that total number of turns and cross section area in a solenoid is fixed. However, its length is varied by adjusting the separation between the windings. The inductance of the solenoid will be proportional to. As few minutes back I told you, the inductance of the solenoid is equal to mu times n square. Mu times n square times volume, and volume can be called as cross section area multiplied by length. As this n is actually the number of turns per unit length. So if we assume the total number of turns as n, we can write a small n as total number of turns divided by length L. Let's replace. We have mu naught n square by L square S times L. And you can cancel one L from here. As total number of turns, the cross section area and the mu naught are constant, we have inductance proportional to 1 by L. Sorry, both have similar symbols. Ignore that. This is inductor. And this is L. You can imagine the L as one, you can replace this by a small L symbol, but they have written the length as L. So just imagine the inductance is proportional to 1 by L. So correct option is D. Okay. Time for next question. Here we have self-inductance, self-induced EMF of a coil is 25 volt. Self-induced EMF of the coil is 25 volt. I think you remember the self-induced EMF in a coil is given by L di by dt. Okay. The current is changed at a uniform rate from 10 ampere to 25 ampere in 1 second. The change in energy stored in the inductor is, that is they are asking. So as the current is changing at a uniform rate from 10 ampere to 25 ampere, I can write di as 25 minus 10 as 50 divided by time is 1 second. So I'll write 1 second and we got inductance as L equals 25 by 15. 25 by 15 Henry. That is 5 by 3 Henry. If we got the inductance, they are saying the change in energy of the inductance. The change in energy of the inductance. Okay, so as energy stored in inductor is half Li square. Okay, so the change in energy would be half L final current square minus half L initial current square. Just calculate the result. We have 1 by 2 L as 5 by 3 times the final current is 25. The initial current is 10. So we have final current as 25 square, that is 625, minus initial current as 10. So 10 square is 100. And you calculate the result and answer will be 437.5 joules. Therefore, the B is your correct choice. Next question. Here we have a long solenoid having 1000 turns. When a current of 4 ampere flows through it, so we have a solenoid of 1000 turns. Total number of turns is 1000. Okay, and the current of 4 ampere is flowing in it. And they are saying the magnetic flux linked with each turn of the solenoid is 4 milliweber. So if magnetic flux linked with one turn is 4 milliweber and there are 1000 turns, the total magnetic flux linked with solenoid would be N times flux with one turn, and you know the total flux is given by L times I. Okay, so let's multiply this. N is 1000 times 4 times 10 to the power minus 3 equals to L, and I is 4 ampere. So solve this and you will get L as 1 Henry. So C is your correct choice. Okay, next question. Here we have a lamp, a fluorescent lamp choke. Actually, choke is a simple inductor. So we have to imagine the choke as a simple inductor. Remember this point. And 100 volt of reverse voltage. What is reverse voltage? Reverse voltage is kind of induced voltage. Okay. So 100 volt of reverse voltage is produced when choke current changes from 0.25 ampere to 0. So actually, just remember the reverse voltage is induced voltage. We can write E as L di by dt. There is a hint also because they are asking you the self-inductance of the choke coil. So write E as 100 volt as they are saying, inductance as L. The change of current is 0.25 to 0. So the magnitude of change is 0.25 and time is 0.025 milliseconds. So I'll write 10 to the power minus 3. And now solve this and I think you will get L as this cancelled. We have 0, 10. So we have 10. 10 multiplied by 10 to the power minus 3 is 0.01 Henry. But as they are saying they want the inductance in millihenry, in millihenry it would be 10 millihenry. So 10 is the right answer for this question. Okay, over to next question. Here we have a coil of inductance 2 Henry and having negligible resistance. So you can assume there is no resistance in the coil and it is connected to a supply, a source of voltage supply whose voltage is given by 3T. So we have almost an ideal inductor having no resistance. If we connect to a source, a voltage source, and the voltage source is 3T and inductor is 2 Henry. So current will start flowing. Let us say at time T, the current in the circuit is I, and let's write KVL for this equation. Okay. So we can write the KVL as V minus L di by dt. As there is no resistance, there is no IR term, we have only these two terms equals to 0. V is 3T minus L is 2 Henry and we have di by dt equals to 0. Let's transfer the results. So we have 3T dt equals to 2 di and now we integrate it. As initially there is no current and let's say at time T the current is I. So we have here 3T square by 2 and here we have 2I. So I equals 3 by 4 T square. I equals 3 by 4 T square. And they are asking us the energy stored in the coil after 4 seconds. As energy stored in the coil is half Li square. So let us first calculate what is the current at that moment. Put 4 here as T as 4 here, you get 12 ampere. And if current is 12 ampere, the energy stored in that inductor would be U equals half L. L is 2 Henry and I square. 2 got cancelled. You have energy as 144 joule. So correct answer is 144 joule. Let's move over to next question. Now we have an inductor again, and this inductor stores 64 joules of magnetic energy. Okay, so this inductor stores 64 joules of magnetic energy. So let us write half L I square as 64 because energy stored in inductor is half Li square. And it also says it dissipates energy at the rate of 640 watt. So if it is dissipating energy, it must be having resistance, and rate of energy dissipation resistance is actually I square R, and this is 640 watt. Okay, and they are asking us if this coil is joined across an ideal battery, as this coil has inductance also, as this coil has resistance also. Why resistance? Because it is dissipating energy. So it will behave like an one loop resistance, inductor and battery circuit, and the time constant of that circuit is obviously L by R, as we have studied. So they are asking us what is the time constant. So we have to tell them the value of L by R. And how you calculate L by R? Simply divide these two equations. If you divide these two equations, I square will be cancelled out. You will be getting L by 2R on the left and 1 by 10 on the right. So L by R is simply 0.2 second. So correct answer is D. Okay. Next question. Here we have a battery of EMF E. Here we have a battery of EMF E is connected to an inductor L and a resistance R in series. The switch is closed at t equals to 0. Now they are asking us the total charge that flows from the battery between t equals to 0 and t equals to Tc. Tc is the time constant. So we have to tell them what is the net charge flown in one time constant. Okay. If you close the switch, I think that's not difficult for you. I think you remember the current in the circuit is given by EMF divided by R and 1 minus e to the power minus RT by L. This is the current expression or current function with respect to time. Okay. As the charge flown can be written as integral I dt by definition. So we have to know the charge flown in one time constant. So let us integrate this function from 0 to Tc. As I is EMF divided by R, and we have I as 1 minus e to the power minus RT by L dt from 0 to Tc. Now it's time for integration. So we have E by R, and this integration will result. Integration of simply 1 dt will be t, and integration of e to the power minus RT by L would be e to the power minus RT by L divided by minus R by L. So this minus will be cancelled out and limits will be from 0 to Tc. What is Tc? L by R, remember. Let's now put the result. We have E by R. First put L by R in the place of T. So L by R. Minus minus became plus. We have L by R times e to the power minus RT by L. So minus R and T as L by R by L. So we have actually e to the power minus 1. We have placed the value of T as L by R, remember, C. And then we have to place the value of the same function at t equals to 0. So at t equals to 0, we have t as 0 and we have this function again, L by R and e to the power 0. As e to the power 0 is 1, so this is finished. You cancel this L by R here and you are left with e to the power minus 1. So we are left with EMF L divided by E and R square. So this is the charge flown in one time constant. Charge flown in one time constant, and let us see what's the answer. So we have D as the correct answer. Okay. So let's move to the next part of the theory. Now let us see what is flux conservation principle. Actually, as you already know that the behavior of inductor, the role of inductor in a circuit is to oppose the change of current. Okay. So if current or flux in a inductor, actually flux is L times I. So if the current wants to change, flux would too wants to change. So if current or flux wants to change suddenly in a circuit, the inductor tries its fullest to oppose that change. So if the current has some path to flow, it will not change instantly. It will not change instantly because the inductor will not let it do so. It can change after a long time, after some time, but instantaneous change in current and flux are not permitted if there is an inductor in the loop. If there is an inductor in the loop, because inductor tries to oppose the change of current. Let me give you one example of it. If I take this a circuit, and suppose here we have a battery and a switch. Initially the switch is on. Let us say this EMF is 12 volt, this resistance is 3 ohm, this resistance is 4 ohms, and we have a 2 Henry inductor. Let us assume this circuit is on from a very long time. So obviously the currents would be in a steady state. Yes. And you know, after a very long time from the starting of the circuit, the role of inductor is just like a conducting wire. So imagine this inductor as just a conducting wire. So because we have 12 volt here, here the current will be 4 ampere and here the current will be 3 ampere, as 12 by 4 is 3 ampere. So in inductor we have 3 amperes current. Okay. And flux in the inductor would be 2 times 3, that is 6 vapor. Suppose suddenly I open this switch. So battery is removed. And if battery is removed, the current in inductor, as it has a path to flow. See, this path is open. This path is open for the current. So the current in inductor will not change instantly. If you are asked what is the current just after opening the switch, you will say here the current will be 3 ampere in same direction. So this 3 ampere would flow in 4 ohm and also in 3 ohm in this direction. Okay. So initially the current in this loop will be 3 ampere just like this. Okay. And later it will slowly change, but initially the inductor will not let the current or flux in that change instantly. This is called the flux conservation principle. Remember this. Now we will study decay of current in LR circuit. Suppose we have a circuit like this and this switch is closed for a very long time. If this switch is closed for a very long time and S2 is open initially, okay, so we have this loop in action. And if this loop is in action, as the circuit is open for a very long time, the behavior of inductor would be simply as a conducting wire, and the current in this circuit will be V by R1. So initial current I naught in the circuit is V by R1. This current V by R1 is flowing from here going into R1 and also flowing in inductor in this way. So we have this current initially I naught. Okay. And what we are doing here, suppose we open this switch S1 and close this S2 simultaneously. Simultaneously we open the switch S1 and close this S2. What will happen then? S1 opened and S2 closed. As the inductor tries to conserve its current or flux when current has a path to flow, see, do the current has a path to flow? Yes, the current has a path to flow. The current was initially flowing in this path, but the current has a path to flow after we change the situations of the switches. So current has a path to flow, and if current has a path to flow, it will not change instantly. So after doing this operation, means opening S1 and closing S2, let us say we did it at t equals to 0. At t equals to 0, we are assuming that instant to be 0 when we opened this S1 and closed this S2. And at t equals to 0, the initial current here is I naught. The initial current here is I naught, and it will decay slowly, but instantly it cannot decay. So when we have a switch like this, a circuit like this, an inductor and a resistance, this is L, this is R, and initial current is I naught. Let us say after some time, the current here is I. And if after some time the current is I, let us apply KVL here. So you apply KVL, you move from here to here, you will have L di by dt. You move from here to here, you have minus IR equals to 0. So you now have di divided by I as R dt by L. Yes, R dt by L. As current here is definitely decaying, because initially we had some current and now it is decaying. So the di by dt we should put a negative sign, and now you integrate this result. As at t equals to 0, we have initial current I naught, which is equal to V by R1, and let's say at t equals to time t, we have current as I. So integrating this equation, you have current as a function of time as initial current I naught times e to the power minus RT by L. The time constant of this loop 2 is L by R, means L by that resistance which is now in the loop. Okay. So time constant is L divided by R, and in terms of time constant you can write I as a function of time t as I naught, which is initial current. You can also call it V by R1 times e to the power minus RT by L, or simply T by tau. This current, as you can see, is decaying exponentially. So the variation of current is like this. Initially we have V by R1 or I naught current in the beginning, and with time the current slowly decays to almost 0. After a very long time you put t equals to infinity here, e to the power minus infinity is 0, so you can see the final current is almost 0. After one time constant, the current is 37% of, or 1 upon e times of, the initial current. So it is I naught by E after one time constant. Okay. Remember one point here, as we have only two elements in the circuit, the magnitude of potential difference across L and the magnitude of potential difference across R is always same, and if we apply KVL here, we have VL plus VR 0 always. Okay, because there is no battery or no such thing in the circuit. So VL and VR are always same in this circuit, and you can write VR as I times R. So VL is also I times R and VR is also I times R. Okay. So we have this question here, and here we have an inductor of 0.03 Henry, resistance of 0.15 kilo ohm, connected in series to a battery of 15 volt EMF. Okay. The K has been kept closed for a long time. The K1 is closed for a long time. So initially you can assume this loop was operating. This loop was operating, and if this loop was operating for a very long time, the behavior of inductor would be simply a conducting wire, and the current, the current here I naught would be I naught would be 15 divided by 150 ohms. So that is 0.1 ampere. You can check. Okay. So it is the initial current going this way. Now when you open this K1 and close K2 simultaneously, they have said the K1 is opened and K2 is closed simultaneously at t equals to 0. So K1 opened and K2 closed. Now as the current has a path to flow, can you see that? As the current has a path to flow, it will not change instantly. It will change gradually, right? And this is a inductor and resistance decaying circuit. And in this circuit, the current as a function of time is given by initial current times e to the power minus RT by L. So let us find current after 1 millisecond. Okay. So I'll put I naught as 0.1 ampere e to the power minus R. How much is R? R is 150 ohms. Okay. And T is 1 millisecond. So RT is actually 0.15 divided by L. L is 0.03. So we get nearly, yes, we get e to the power minus 5 here. E to the power minus 5 here. So I can write I as a function of time as 0.1 divided by e to the power 5. And e to the power 5 is 150 here. So the value becomes 0.1 divided by 150. Okay. If you try to find current in milliampere, so multiply this by 1000 and you will get 100 divided by 150, which is 2 by 3 milliampere. And obviously 2 by 3 is 0.67. So we have current as 0.67 milliampere and B is the rightest choice. Okay. So let's move. Yes. Now we have to study LC oscillations. We have to study such circuits where we do not have resistance. We have inductor and a capacitor. We have inductor and a capacitor. So suppose, let me tell you the initial conditions. Suppose I am taking initially that we have a capacitor, we have a charged capacitor. Let's say charge on the capacitor is Q naught minus Q naught, zero current here. Okay, but as there is charge on capacitor and charge has a path to flow, it will flow. And when the charge flows here, let's say after a time t, the charge on capacitor is Q minus Q and the current in the inductor, current in the circuit is I. As initially there is no current, the current I must be increasing definitely. So if we write KVL here, let's write KVL here. The KVL can be written as, start from here. You are going from negative to positive side, so potential must increase. I'll write Q by C, where C is the capacitance, and minus L di by dt minus L di by dt equals to 0. This is the basic equation for LC oscillating circuit. Why it is called oscillations? Let me tell you slowly. So, can you see the current is going away from the positive plate, and if current is going away from the positive plate's charge must be decreasing, and if charge of positive plate is decreasing, you can write current as minus dq by dt, because current would be the rate of change of charge. Okay, here. So as charge is decreasing, the current is equal to negative of rate of change of charge or the rate of decrease of charge. So I am writing I as minus dq by dt. Okay. So let me replace I by minus dq by dt here, and you will have q by c equals minus L d by dt of I, and I is minus dq by dt. I have placed minus sign, so dq by dt, right? So what we have is, see, you have d2q by dt square as minus 1 by LC times q. Okay. So the second derivative of charge is depending upon the charge itself, and it is proportional to minus q. If you think of this relation, a very popular and interesting relation will strike your mind, and that is d2x by dt square equals to minus omega square x. You must have studied this type of equation in SHM. And as this has a similar form as this, the solution of q would be same as the solution of x here. And since the displacement varies sinusoidally in SHM, the charge also will vary sinusoidally in SHM. Okay. So I can write the charge as q times sine omega t plus phi. What is q? Q is obviously the maximum value of charge, right? Q is maximum value of charge. And what is omega? So omega you can find by comparing this with this. Can you see at the place of omega square we have 1 by LC. So omega is simply 1 over root LC. So this is the angular frequency according to which the charge varies periodically in this circuit. And as the equation resembles with equation of oscillations, we call it LC oscillations. Okay. The value of phi will be found by initial conditions. Okay. So what are initial conditions? As you know, initially when we put t equals to 0, the charge was maximum. This was the initial condition we took in this problem. So you put, just look at the equation. As we assumed at t equals to 0, the charge is maximum on the capacitor. So maximum charge is represented by q naught. So I can write at t equals to 0, at t equals to 0, the q is equal to q naught, and you will get sine phi equals to 1. That is phi equals to pi by 2. Okay. So the variation of q will be like q equals q naught sine omega t plus pi by 2 becomes cos omega t. If you want to find what is current, the current would be minus dq by dt, and if you calculate minus dq by dt, you will get q naught omega and sine omega t. So here the charge and the current both vary sinusoidally. Okay. Obviously there is a phase difference, and you can see the phase difference between variation of charge and variation of current is pi by 2. Here in this case, the phase difference is pi by 2, but that doesn't matter. The main point is the charge and current vary sinusoidally. And the angular frequency of variations is given by 1 over root LC. Remember this formula, that is very important. And there is one very important point here. As this circuit had no resistance, the energy that you have given in the beginning cannot be lost. the energy cannot be lost. Okay. So can you see the initial energy? We had no current, so energy in inductor is zero. But initially capacitor had some energy. In this case, capacitor has Q naught square by 2C energy initially. Okay. And if after some time the capacitor has charge Q, the inductor has current I. So at any point of time, you remember energy is conserved in circuit. Energy is constant in circuit. So at any time t, if charge on capacitor is a small q, so q square by 2c is energy of capacitor, energy with capacitor, plus half L I square. It is the energy with inductor, and this sum will remain constant and it will be equal to initial energy given to the system. It is equal to, and initial energy given to system was Q naught square by 2C, so it will remain a constant and equal to initial energy, remember. Okay, so that is a very important point with this circuit. As there is no resistance, the energy cannot dissipate, and that is why the total energy of capacitor plus inductor will remain same and will be same as the initial energy that you give into. Okay. So we have a very important problem based on this, and it says an ideal capacitor of capacitance 0.2 microfarad is charged to a potential difference of 10 volt. So we have a charged capacitor and it is charged to 10 volt. It is connected to an inductor, ideal inductor of inductance 0.5 millihenry. So it is connected to an inductor of 0.5 millihenry, and obviously the capacitor is ideal, the inductor is ideal. It will be behaving like an LC oscillating circuit. Okay, they are asking us what is the current? What is the current at time when potential difference across the capacitor is 5 volt? As you know, the energy in this system remains conserved. So let us say at the moment the capacitor's potential is 5 volt, the current is I. And if current is I, the energy in inductor would be half L I square. Energy on capacitor would be half C V square. The capacitor voltage is 5 volt, so we have 5 square equals to, this energy will be equal to the initial energy. And initially we had energy on capacitor only. Okay, so on capacitor we had initial energy as half C and 10 square. Now we know the value of C, we know the value of L, only the I is unknown, and if you solve I, you will find I nearly as 0.17 amperes. Okay, so the correct choice is A. So now let's move. After self-induction, we will study mutual induction. And as self-induction was induction because of its own current, mutual induction is the induction because of some other's current. So name 2 is also very simple. Suppose we have two coils here, and this is coil C1 and that is coil C2. Let us assume some current I1 is flowing in coil 1. Okay, I1 is flowing in coil 1. Obviously, when I1 flows, the coil C1 will develop some magnetic flux, and some of its flux will also link the coil 2. Okay, so if there are some changes in I1, the flux linked with coil 2 will also change. Okay, or you can say the total flux created by I1, some part of the flux is linked with coil 2, but the flux linked with coil 2 is because of the current in coil 1. So let me write, if I'm trying to write the flux linked with coil 2, we can see this flux is proportional to the current in coil 1. because this flux is because of the current in coil 1. If I add a constant of proportionality, I can write phi 2 as equal to M21. M is called coefficient of mutual induction. The unit is Henry, and it is mutual induction coefficient of second coil 2 with respect to 1 or due to 1 and I1. Okay, so this is the flux linked with coil 2 because of current in I1. Okay, suppose we think the other way. If I make some current to flow in coil 2, it will too create its own flux, and some of its flux will also link coil 1. So flux linked with coil 1 will be proportional to current in coil 2, and this will be written as flux 1 equals M12 I2. There is a very amazing result that you should remember, and that is M21 always equals M12. Means if you have some current in coil 1 and we have some flux with coil 2, if I make the same current to flow in coil 2, the flux linked with coil 1 will be same as the previous flux linked with coil 2 when the current was in coil 1. So remember this fact, always remember this fact, that this can be written as simply M. Let us interpret it a little more. What it says actually. Okay, it says, suppose the current in coil 1 is say 10 ampere. That creates a flux around it, and because of this 10 ampere, the flux linked, this is coil 1, this is coil 2. The flux linked with coil 2 is suppose 5 Weber. 5 Weber. Okay, remember. Now the principle says, this result says, this is an experimental result based upon some theorems which are beyond the scope of our course, but remember this, M21 and M12 is same. So it says, if coil 1 has a current of 10 ampere and there is a 5 Weber flux with coil 2. Okay, if you make the 10 ampere flow with coil 2, if you make 10 ampere the same current flow with coil 2, the flux with 1 ampere would be 5 Weber. Okay, so if you have same current here, you will have same flux here, and that is because M21 is same as M12. So there is no need to write M21 or M12. We simply write M only, and it is not depending upon the shape and size of coil. They may be different, but M for 1 with respect to 2 will be same as M for 2 with respect to 1. Okay, so remember this. And one more point is there. If say flux with coil 2 is equal to M times I1. If current changes, if suppose current in coil 1 changes, the flux linked with coil 2 will also change because current is changing. And because of this flux change, an EMF is induced, and that EMF is called mutual induction EMF. So E2 will be actually minus d phi 2 by dt, and can be written as minus m di1 by dt. So if two coils are mutually linked, they are placed close to each other, and in one coil's current changes, we see some induced EMF in other coil also. And similarly, if the current of coil 2 changes, EMF will be induced in one, and that will be equal to minus m di2 by dt. So that is the concept of mutual induction. Okay, so let us solve some problems based on this. It says there are two long coaxial solenoids. There are two long coaxial solenoids of same length. So we have one solenoid like this, and the inner and outer coils have radii. So the radii are different actually. So I am taking the other solenoid as this, and radii of one is R1 and radii of other is R2 actually. The number of turns per unit length are N1 and N2. So let's say here the number of turns are N1 per unit length, here the number of turns are N2 per unit length. And they are asking us the ratio of mutual inductance to the self-inductance of inner coil. So let me write the self-inductance of inner coil. The self-inductance of, okay, there is a little mistake. Actually, the inner coil's radius is R1, the outer coil's radius is R2. So let us flip the result. We have R1 this and R2 this. We have N1 this and N2 this. So inner coils radii is R1 and number of turns per unit length are N1. So as you know, the inductance is mu naught N square. Inner coils radius is R1 and number of turns are N1. So mu naught N1 square and then volume. Volume is cross sectional area times length. So cross sectional area is pi R1 square and length is L. So this is self-inductance of inner coil. Now we have to calculate the mutual inductance. Let me tell you the method to calculate mutual inductance. The method is simple. Make some current flow in any one coil. So let us flow some current I in inner coil. Okay, let some current I is flowing in inner coil, and because of this current, the magnetic field will be produced. The magnetic field produced will be equal to mu naught N1I, and try to find flux linked with outer coil or the second coil. So flux through one turn of outer coil would be, let us see, as the magnetic field is this, the magnetic field is confined in the inner coil only. As you know, outside this there is the magnetic field, because of solenoid, outside it is almost zero. So we have magnetic field in the inner region only, because we have flown current in the inner coil only. So magnetic flux will be equal to B times area. The B is mu naught N1I, and area is simply pi R1 square, because the magnetic field is present only in this inner region. Okay. If I calculate magnetic flux through outer coil, the magnetic flux will be same as this, because outside R1 we have zero magnetic field. So the same magnetic flux will be shared by outer coil. As this is the magnetic flux with one turn of the coil, let us say length is L. Let us assume the length is L. So the total number of turns in outer coil will be N2 times L. And this is actually the total flux with outer coil, and it is depending upon inner coil. So as total flux with outer coil is equal to M times I, so by comparing the result, you can notice the M equals, let us see what is M equals. The M equals, compare these two results, ignore the current I, then M equals mu naught N1 N2 pi R1 square L. Okay. So let me write mu naught N1 N2 pi R1 square L, and inductance was actually mu naught N1 square pi R1 square L. So as they are asking us the ratio of M to L, the M by L would be equal to, if you cancel everything, you will left with N2 by N1 only. So that is the required ratio, and the correct option is D. Next question. Here we have two coils and they are separated by some distance. When current of 3 ampere flows through coil P, so let us make these two coils P and Q. Yes. When current of 3 ampere flows through coil P, we have 3 ampere current flowing through coil P. A magnetic flux of 10 to the power minus 3 Weber passes through Q. So flux through Q is equal to as M times I1 or IP, I must say. We now know the value of M. As flux is 10 to the power minus 3, I is 3. So M equals 10 to the power minus 3 divided by 3 Henry. Now they are saying when no current passes through P and a current of 2 ampere passes through Q. So if current of 2 ampere passes through Q, the flux through P will be. So as you know, the flux through P is equal to the same M we obtained earlier, because M21 and M12 are same as I explained earlier. So flux through P would be equal to M times IQ, and let us write the value of M as 10 to the power minus 3 divided by 3 times 2. You will have, I think, A as the right result, because it is 0.67 times 10 to the power minus 3 and it is 6.67 multiplied by 10 to the power minus 4 Weber. So option A is the perfect choice. Next. Here we have two concentric circular coils, C1 and C2, and they are placed in XY plane. So suppose we have XY plane here and we have two coils C1 and C2. The C1 has 500 turns and a radius of 1 centimeter. So we have a very tiny C1. It has 500 turns and 1 centimeter radius. And C2 has 200 turns and a radius of 20 centimeters. So C2 is quite big. C2 has 200 turns and 20 centimeter radius. C2 carries a time dependent current, and that current is given by this function where T is time. What is the EMF induced? They are asking us what is the EMF induced in the coil C1 at T equals to 1 second. Okay. Let us calculate. If current is flowing here, I, obviously it will create a magnetic field near center, and the magnetic field is given by mu naught I divided by 2R, and as there are 200 number of turns, let us write 200 as N2. So the net magnetic field would be mu naught I N2 because divided by 2R, where R is, you can say R2, as R2 is 20 centimeter, right? Okay. Actually, this is the magnetic field produced at the center. But as the area of the first coil is so small, is very small, we can assume this magnetic field is almost uniform over the small area, and we can assume the magnetic field uniform over the area of a smaller coil. Okay, so flux, the total flux linked with a smaller coil would be B multiplied by area of a smaller coil is pi R1 square, and multiplied by number of turns. Let's say number of turns are N1, so we place N1 here. This is the magnetic flux. Okay, let me write the value. The B would be mu naught N1 N2. We have pi, we have R1 square, and we have I. Let us see. B is pi R1 square. We have covered pi R1 square. We have covered N1, and at the place of B we have mu naught I N2. Mu naught I N2. Everything is covered and divided by 2R. This is the flux through the smaller coil, and as the current is changing, the flux would change, and the flux changes, the EMF is induced. So the EMF induced, the magnitude of EMF induced is actually the rate of change of phi, which is d phi by dt. And if I calculate d phi by dt, let me write all the constants, which are mu naught N1 N2 pi R1 square mu naught, this is R2 actually. So mu naught N1 N2 pi R1 square, mu naught N1 N2 pi R1 square divided by 2 R2 and di by dt. And di by dt you can calculate from this function. Here by differentiating with respect to time, you have di by dt as 10t minus 2. So we have 10t minus 2. Now they are asking us what is the magnitude of EMF induced at 1 second. So what we have to do, we have to just place the value of time as 1 second. Put all the values here. You know the value of mu naught, N1, N2, they are 200 and 500. R1 is 1 centimeter, R2 is 20 centimeter. You know the value of pi and time as 1 second. You calculate this carefully and you will find the correct answer of EMF as 0.8. Okay. You will find the EMF as 0.8 volt. But as they are asking as the EMF is 4 by x and they are asking us the value of x. So if you make this equal to 4 by x, x would be 4 upon 0.8, so x will be 5. So the answer they are asking is, to keep the length of the sessions uniform, I am taking some part of the magnetism here in this chapter and some part of this chapter will be taken in the next chapter, which is alternating current. Okay, so now we will study about permanent magnets. I'm sure you all are aware about permanent magnets. We have played with them from the childhood. They are of many shapes. Sometimes we see circular magnets, sometimes we see disc type magnets, but the most popular is a bar magnet. What is a bar magnet? The bar magnet is just a bar-like magnet with two poles in it. One is south pole and one is north pole. Okay, let us say the length of this magnet is the length of the magnet is L. We can compare this with an electric dipole where we used to have a negative charge minus Q and a positive charge plus Q placed at some separation L. And here we used to define electric dipole moment vector as Q times L from negative charge to positive charge. Let's say this is some unit vector from negative charge to positive charge. So we used to define electric dipole moment as QL times N cap. Similarly, we can also assume that here we have some kind of negative magnetic charge and here we have the kind of positive magnetic charge. So here we have negative magnetic charge called minus M and here we can assume we have positive magnetic charge plus M. Also, as the density of magnetic field is greatest at these points, assumption of these concentrated poles is valid. Okay, so now we assume that we have in the place of a magnet, we have two poles or two magnetic charges, one negative magnetic charge and one positive magnetic charge. This M is called magnetic charge or pole strength. Yes, pole strength. And here the magnetic dipole moment is defined by M times L, right, and multiplied by a unit vector from negative magnetic charge to positive magnetic charge, that is from south pole to north pole. So we can compare an electric dipole with a magnetic dipole like this, and similar to electric dipole moment, we have magnetic dipole moment equal to M times L, where M stands for magnetic charge or pole strength. Okay, I think you remember the magnetic moment of a coil of a current carrying coil was N, the number of turns, I and A. So unit for magnetic moment is actually ampere meter square, because this is area, so it is ampere meter square. So if it is ampere meter square, we have one length here, so unit for pole strength or magnetic charge becomes, the unit becomes ampere meter. So always remember this point, and this is a little bit about bar magnets. Okay. So as we used to put an electric dipole in some electric field, the dipole used to experience a torque. Similarly, if we place a bar magnet in a magnetic field, it also experiences a torque. So suppose we have a magnetic field like this, B, and we have a bar magnet. Its magnetic moment is M, and the angle between them is theta. The bar magnet also experiences a torque given by M cross B. M cross B, or the magnitude is given by MB sine theta. So always remember the direction of torque will be such that it will always try to bring the magnetic moment along magnetic field. Okay, so in this case, the torque will try to bring magnetic field along magnetic field. So this kind of clockwise torque will act on the magnet in this case. But if we have magnetic field and magnets like this, we have magnetic moment like this. Here again, the purpose of torque would be to bring magnetic moment along magnetic field, but here the torque will be anti-clockwise, because then only it can bring magnetic moment along magnetic field. So remember, this is the formula for torque in magnetic field on a bar magnet. If you just place a bar magnet in magnetic field, okay, it will try to align in the direction of magnetic field, because the torque tries to align the magnet along magnetic field. So whenever you place your magnet at some angle with magnetic field, the torque brings it along magnetic field. But here it develops some kinetic energy and overshoots in this direction, and then it makes some oscillations. Okay. If theta is small, if theta is small, yes, if theta is small, then the oscillations are nearly SHM. It executes SHM, and please remember the time period of SHM is given by 2 pi square root of I, where I is moment of inertia of this magnet about rotational axis, divided by magnetic moment multiplied by magnetic field. So this is the time periods formula. Also, as electric dipoles used to have some potential energy in electric field, here also the magnets too have some potential energy of interaction with magnetic field. So if we have a magnetic field and magnetic moment makes angle theta with it, the potential energy is given by minus m dot p. Or you can say the potential energy is given by minus m b cos theta, where theta is equal to, the theta is the angle between magnetic field and the magnetic moment. If I draw this potential energy versus theta, okay, so as you know, the cos theta curve starts from here and goes like this. So minus cos theta would be something like this. This is the variation of potential energy versus theta. Okay. These angles are 0, pi, and this is pi by 2, 3 pi by 2, and 2 pi. So notice when magnetic field is magnetic field and magnetic moment are in same direction, the angle between them is 0, potential energy is minimum. And if potential energy is minimum, the torque is 0, because if theta is 0, the torque is 0, because sine theta is 0. So, when we have our magnet aligned along magnetic field, in this case we have torque equals to 0 and potential energy minimum. The 0 torque indicates that magnet has no torque, means magnet is in rotational equilibrium. The magnet is in rotational equilibrium, and minimum potential energy says the equilibrium is a stable one, a stable equilibrium. But at this point where theta is pi, means magnetic moment and magnetic field are in opposite direction. Magnetic moment like this, magnetic field like this. Okay. In this case also the torque will be 0, as angle between M and B is 180 degree or pi radius, and sine pi is also 0, so torque is 0, but potential energy is maximum. So here again we are getting equilibrium, but as potential energy is maximum, the equilibrium will be an unstable one. Unstable equilibrium. So remember these points. Now we will study about the magnetic field produced by a bar magnet. So it is again very similar to the electric field produced by a short electrodipole. The only condition that we have here, the magnet should be small. So if magnet is small means small means as compared to the distances at which we are trying to find magnetic field, that the size of magnet should be very small. So suppose we have a tiny magnet here, its magnetic moment is m, then the line of magnetic moment is called the axis of the magnet. It is called the axis of the magnet, and the line that cuts the magnet in two parts perpendicularly is called transverse axis. This is transverse axis. If I rotate this line perpendicularly to the magnet, it will convert into a plane that will divide entire magnet into two parts, and that plane is called equator. That plane is called equator. Okay. So remembering formula is also very simple. If you wish to find magnetic field at a distance r from magnet on axis, the magnetic field is parallel to magnetic moment. Always remember, the magnetic field is parallel to magnetic moment. Even at these locations also, if can you see magnetic field is, the magnetic moment is towards right, so here also magnetic field will be towards right. So on entire axis, the magnetic field is in the direction of magnetic moment, and on axis the magnetic field formula is (2k m by r cube). 2k m by r cube. What is r? R is the distance from magnet to the point, m is the magnetic moment, and k is your famous mu naught divided by 4 pi. I think you remember, on the axis of an electric dipole, we had electric field as 2kp by r cube. This formula is exactly similar to that formula, where k used to be 1 upon 4 pi epsilon naught, the famous constant of electrostatics, where p used to be the electric dipole moment, here m is magnetic dipole moment, and r is the distance. Okay. So remembering this formula is really very simple. If you wish to find magnetic field at a distance r from magnet on transverse axis, just like electric field of dipole, here also the magnetic field is opposite to magnetic moment. The magnetic field is opposite to the magnetic moment on transverse axis, and this magnetic field on transverse axis or on equator is Km by r cube. Km by r cube, and I think you remember the same formula we obtained for electric dipole's magnetic field on equator, where we had Kp by r cube, but the P was magnetic dipole moment. Okay, so remember these laws, they may be very useful for you if you find a question related to this. So let us solve a question on this, and here we have a small bar magnet placed with axis at 30 degree with an external field of 0.06 Tesla. So we have a magnet, we have a magnetic field, and we have a magnet, and magnet's dipole moment, it is at angle 30 degree with magnetic field. It experiences a torque of 0.018 Newton meter. As torque is equal to mb sine theta, we can write 0.018 is equal to mb sine 30. And what is sine 30? 1 by 2. That is our first equation. Let us put it here. Now they say, what is the minimum work required to rotate it from its stable to unstable equilibrium position? As you know, the work required is equal to final potential energy minus initial potential energy. Okay, and as finally it is in unstable equilibrium position and initially it is in stable equilibrium position, please recall the formula. Yes, in case of unstable equilibrium, the potential energy is maximum, and the maximum potential energy is simply mb, and at stable equilibrium position the potential energy is minus mb. Okay, so as initially the dipole is in a stable equilibrium position, and finally in unstable equilibrium position we have final potential energy as plus mb minus initial potential energy as minus mb. So we have work done as 2 mb. I'll just bring the value of mb from here. Can you see mb is 2 times torque? So mb is 2 times torque. We have 2 here, so we have 4 times torque. And what is torque? Torque is 0.018. You multiply this and you will have 7.2 times 10 to the power minus 2 joule. Okay, so that is your correct answer, and you can find this answer in C. So correct choice is C. Okay, over to next question. Here they are asking us, a dipole is in a constant magnetic field. Dipole is in constant magnetic field has, and we are given 4 options. We have to check every option. They are saying maximum potential energy when torque is maximum. Let us write torque and potential energy formula. The torque is mb sine theta, and the potential energy is minus mb cos theta. So if you check option A, the maximum potential energy is obtained when theta is pi, because that moment you will be plus mb. So maximum potential energy, for maximum potential energy, theta should be pi. And if theta is pi, the torque should be 0, because sin pi is 0. Means the potential energy is maximum when torque is minimum. But they are saying the maximum potential energy when torque is maximum. It is wrong. Okay, then let us check the option B. 0 potential energy. The potential energy will be 0 when cos theta will be 0, and when it happens when theta is pi by 2. So we have zero potential energy when theta is pi by 2. And when theta is pi by 2, sine pi by 2 is maximum. So actually potential energy will be zero when torque is maximum. And let us see where it is written. Yes, in option C, it is written that zero potential energy when torque is maximum. So C is your correct choice. Let us also check D. Minimum potential energy when the torque is maximum. If you find about minimum potential energy, it will be minus mb, and that you will get when theta is 0. And when theta is 0, torque is not maximum, it is actually 0. So D is also incorrect, and the correct choice is C. Now we will learn about Earth's magnetic field. I think you all know that Earth also has its own magnetic field. Earth also has its own magnetic field. Initially, we did not know the reason behind Earth's magnetic field. People used to say there is a giant big magnet inside the Earth. But now we know the magnetic field of Earth has lots of contributions from lots of factors. The biggest contribution is from, actually in the core of the Earth, we have ionized molten metals. And when Earth spins, these ionized molten metals spin along with Earth. And when they spin, they form lots of big circular currents. And these rotating currents, these moving currents, they are similar to a solenoid, and then the entire Earth becomes a big giant magnet, and we have its magnetic field. So let me tell you few important points about Earth's magnetic field. Okay. This vertical line is actually the geometric axis of the Earth, and about this the Earth is rotating. So the axis about which Earth rotates, Earth spins, is called geometric axis, and this geometric axis cuts the Earth at 2 points. One is called the geometric north pole, and other is called the geometric south pole. But a very interesting thing happens about the magnetic field of Earth. The magnetic field of Earth is or has its axis not along the geometric axis. The axis of magnetic field, or you can say the assumed magnet inside Earth, has its axis at some angle with the geometric axis, and that angle is nearly 11.5. So Earth has its magnet. You can assume that Earth has its magnet at some angle with the geometric axis, and that angle is 11.5. Okay. Close to North Pole, we have South Pole of the magnet, Earth's magnet, and close to South Pole we have North Pole of the magnet. But we call this as geometric North Pole. We don't call it we call it the magnetic North Pole, and we call this as magnetic South Pole just because they are close to geometric North and geometric South poles. Okay, so remember this point, Earth actually has its South Pole near to North Pole, the geometric North Pole of Earth, but we call this point as the magnetic North Pole only. Okay, the reason is it is very close to North Pole of the Earth. Okay, so this is the magnetic axis, and the magnetic field lines emit from North Pole of the Earth's magnet. They move like this, and they re-enters the Earth from South Pole and enter into the Earth back. As they are being emitted from the South Pole, you can say the magnetic field at South Pole is vertically outward, I must say, and magnetic field at the North Pole also vertically inward. Okay, and at the place of equator we have almost horizontal magnetic field. At the place of equator, because of the symmetry, if you draw a line dividing the Earth into two parts magnetically, this will be magnetic equator. It is magnetic equator. It is magnetic equator. Okay, and as the magnetic field of Earth is symmetric, the magnetic field is almost horizontal at magnetic equator. Okay, but let me repeat this. At the place of poles, at the place of magnetic poles, we have vertical magnetic field. At the place of equator, we have horizontal magnetic field. But at all other places, the magnetic field is neither purely vertical or nor purely horizontal. It is at some angle with horizontal, and that angle has lots of importance in this chapter. So that is a little bit about Earth's magnetic field. Let us learn few more points about Earth's magnetic field. Okay. So we have three major elements of Earth's magnetic field. The first is horizontal component of Earth's magnetic field. Horizontal component of Earth's magnetic field, and this is known as BH. We call Earth's magnetic field as B, so horizontal component is called BH. The second point is angle of dip. This is called theta. Let us understand what is angle of dip. As I told you that at poles magnetic field is vertical. At equator, at magnetic equator, the magnetic field is horizontal. But at all other places, magnetic field is inclined with horizontal. Okay. If we check any place in India, we have magnetic field inclined with horizontal and a little on lower side with horizontal plane. This is the magnetic field of Earth. And the angle the Earth's magnetic field makes with horizontal plane, this is actually horizontal plane. So the net angle the Earth's magnetic field makes with horizontal plane is called theta, the angle of dip. The angle of dip. So we can say we have two more components of magnetic field, one horizontal component of magnetic field, one vertical component of magnetic field, BV. And we can write few relations from here, with few trigonometric relations from here. One is tan theta equals BV upon BH. You can write many more as sin theta equals BV upon B, cos theta equals BH upon B. Like you can write many equations from here. This is angle of dip. And the third and last element of Earth's magnetic field is angle of declination, delta. Let us understand this angle of declination. Suppose I look at the geometric north of the Earth, right? So if I have the geometric north of Earth like this, we will be having east direction like this. So suppose this hand is towards north, so this is the north-south line. This is actually, this hand's line is north-south line, and this is east-west line. This is east-west line, and they both are horizontal. So this is your horizontal plane. Okay, this is your horizontal plane. Okay, remember this is north-south line. This line is north-south line. So actually the Earth's magnetic field is not in this line. Is not in this line. The Earth's magnetic field actually makes some angle. The Earth's magnetic field makes some angle with north-south line. Okay, and as it is inclined with horizontal, it is a little downward. So Earth's magnetic field is something like this. From horizontal plane, the Earth's magnetic field makes an angle theta. So this angle is actually theta. This is called angle of dip. Okay. This plane in which we have Earth's magnetic field, the plane in which we have Earth's magnetic field, the vertical plane, I must say, the vertical plane in which we have Earth's magnetic field is called magnetic meridian. Remember this point. I'm writing in the next page, but remember this point. The plane in which we have Earth's magnetic field is called magnetic meridian. And the vertical plane in which we have north-south direction, we call it geometric meridian. And as these two meridians, the two planes are different. We have magnetic meridian in the plane of magnetic field of Earth, and we have geometric meridian in which we have north and south directions. Both planes are vertical, but both are at some angle with each other. The angle between geometric meridian and magnetic meridian is called angle of declination, delta. The angle between magnetic meridian and geometric meridian is called angle of declination. Angle between geometric meridian and magnetic meridian is called angle of declination. Let me re-explain this with this diagram. Okay, suppose this is north-south line. This is north-south line. Okay, and if this is north-south line, we can imagine a vertical plane passing through north-south line. Can you see this? This is the vertical plane passing through north-south line. This vertical plane is actually called geometric meridian. This is called geometric meridian. We have magnetic field of Earth in this plane. Can you see? In this plane. And magnetic field of Earth is dipped by some angle, a theta called dip angle from horizontal, but this is in this plane. And this plane makes angle theta with geometric meridian, and this plane is called magnetic meridian. Okay, so we have geometric meridian as vertical plane passing through north-south line. We have magnetic meridian as vertical plane containing the magnetic field of Earth, and the angle between them is called angle of declination. We also have one more vertical plane, this having east-west direction. This vertical plane, it doesn't have any name in this chapter. So I think you got this point. Okay, and please notice the angle of dip is given by vertical component of magnetic field divided by horizontal component of magnetic field. Okay, so let us understand a simple idea that if you go in magnetic meridian, suppose you find magnetic meridian, suppose this is magnetic meridian. If this is magnetic meridian, you just hang a magnet in magnetic meridian. Okay, the magnetic field of Earth is in magnetic meridian. So if you just hang a magnet which can rotate in any direction, it will definitely point towards the magnetic field of Earth. Suppose we have a small needle, okay, that it can move in vertical plane. Suppose we have a small needle that can rotate in vertical plane, it will automatically be aligned along magnetic field. Its magnetic movement will be aligned along magnetic field, and obviously the angle that this needle makes with horizontal will be angle of dip. So measuring angle of dip is very small. Just placed a magnetic needle that can rotate in vertical plane. Just place this magnetic needle in magnetic meridian, and the angle the needle makes with horizontal is actually the angle of dip. And you can call this angle tan theta as BV by BH, or cot theta as BH by BV. But what if you are unable to find where is magnetic meridian? What if you are unable to find where is magnetic meridian? Suppose the exact meridian, magnetic meridian, is this. I'm looking at top view. Notice please, I'm looking at top view. Okay. So the magnetic meridian just looks like a straight line, but the magnetic meridian is a plane passing through this line in vertical direction. But the problem is the magnetic needle is placed in some other plane. The magnetic needle is here and it is placed in some other plane, and this angle alpha we do not know. If we see the angle of dip in this plane, that angle of dip will be untrue, because the true angle of dip can only be obtained in magnetic meridian. So if you notice the angle of dip here, it will be untrue. As magnetic field has horizontal component in magnetic meridian, so this is BH, and say vertical component in downward direction BV. If you bring that needle in this plane, it will give you true dip. Suppose theta is the true dip. But suppose you do not know where is magnetic meridian. You have just placed your magnetic needle here in this plane. So the angle of dip would be untrue. Let us see what is the untrue, what is the wrong or apparent angle of dip. Let us write cot theta 1 as cot theta is given by BH upon BV. But here in this plane, the BH will have its component BH cos alpha. So at the place of BH, we'll be having BH cos alpha divided by BV, as full the vertical component is along vertical direction. So it will contribute its full value in any plane. Okay. What we have to do next, let me write this somewhere else, someplace else. Yes. Cot theta 1 equals BH cos alpha divided by BV. It's very simple. The cot theta is BH upon BV, but in this plane, the apparent dip will be equal to the cot theta 1 will be equal to BH along this plane divided by BV, and BH along this plane is BH cos alpha. What we have to do, we don't have to find this plane, just rotate your plane of the coil perpendicular to the initial plane. Just rotate your coil perpendicular to the initial plane so that it turns by an angle 90 degree, and measure one more apparent dip here. If you measure one more apparent dip, cot theta 2, in a perpendicular plane than initial one, we measured apparent dip in this plane. This is not magnetic meridian. Just measure apparent dip in one more plane which is perpendicular to the initial plane. And here the cot theta 2 would be BH upon BV. But in this plane, the BH component would be BH sin alpha. BH sin alpha divided by BV. Okay. Now we have measured two apparent dips in two mutually perpendicular planes, vertical planes, but none of the plane is magnetic meridian. Can we find true dip? Let us see. If I take these two equations, square them and add them, we have cot theta 1 square plus cot theta 2 squared equals, you have BH square by BV square, and inside bracket you have cos square alpha plus sin square alpha, and cos square alpha plus sin square alpha is always 1. So this equals actually the cot square times cot square true dip. So remember this formula: by measuring two apparent dips in two mutually perpendicular planes. None of them is magnetic meridian, but still by measuring these two apparent dips and using this formula, you can find the true angle of dip. Okay. So remember this point. This was once asked in some years NEET exam directly. They simply wrote 4 options and the one correct option was this one. Okay. So let us solve few questions based on this. This question says, at some location on Earth, the horizontal component of Earth's magnetic field is 18 times 10 to the power minus 6 Tesla. At this location, a magnetic needle of length and pole strength, means pole strength is also given, and it is suspended from its midpoint using a thread, and it makes angle 45 degree with horizontal. So what does this mean? If we suspend a thread, if we suspend a needle with a thread and it is pointing at an angle 45 degree with horizontal, obviously it is in magnetic meridian and the needle is pointing towards net magnetic field of Earth. Net magnetic field of Earth, it is pointing towards net magnetic field of Earth, and this is actually angle of dip. So we have theta, the angle of dip, as 45 degree. As we know, the BH is known to us. BH is known to us. We can calculate what is true magnetic field at that location of Earth, and we can write B as BH upon cos 45. So it will be BH root 2 because cos 45 is 1 by root 2. So net magnetic field would be BH root 2. Now they have said something else. Now they say, to keep this needle horizontal, the vertical force that should be applied at one of its end will be. So if someone pushes one end of the needle to make it horizontal, and suppose the needle becomes horizontal, okay, but the magnetic field is still at 45 degree with horizontal. Let's say magnetic moment of the needle is M. So to keep this, we have to put a force F, and the force will be equal to, at a distance L by 2 from the center. Obviously the length of the needle is L, so force will be at a distance L by 2 from center, and obviously the magnetic torque will be like this, and the force torque will be opposite to it, and the two torque must balance to keep the needle horizontal. The torque of force would be F times L by 2, and the torque of magnetic field would be MB sine 45. MB sine 45. I can write this again, F times L by 2 equals M. M can be written as the pole strength times the length, and B sine 45 can be written as 1 by root 2. So 1 by root 2, and L got cancelled. Now you know the pole strength, and the pole strength is 1.8 ampere meter. You know the magnetic field, we have magnetic field, and we know everything here to find force. And if you calculate, the force would be root 2 times M times B, and you will find the force is nearly equal to this value, 1.6 times 10 to the power minus 5. Okay, so the correct choice is D. Next question. Here they say the magnetic compass. I think you all must have seen magnetic compass, and in magnetic compass, just try to imagine the needle rotates in horizontal plane. So if needle rotates in horizontal plane, it will align itself along horizontal component of magnetic field. Okay, so a magnetic compass needle oscillates 30 times per minute at a place where dip is 45 degree. Okay, let me remind you the formula for time period. The time period was 2 pi square root of I divided by mb. But as the needle can rotate in horizontal plane, it can only respond to horizontal magnetic field. So at the place of magnetic field, I should write BH. As in the first condition, it oscillates 30 times in 1 minute. So I can write the time period as 60 divided by 30 equals 2 pi times square root of I divided by m, and initially the magnetic field is B. The magnetic field is B1 actually, and the angle of dip is 45. So horizontal component can be written as B1 cos 45, and cos 45 would be 1 by root 2. So that is the first equation. In second case, at some other place where magnetic field is B2 and angle of dip is 30, it makes 40 oscillations per minute. Okay, and if 40 oscillations per minute, the time period will be 60 seconds divided by 40 equals to 2 pi square root of I by m. But this time horizontal magnetic field would be B2 cos 30. Remember, B2 cos 30. So I should write B2 and cos 30. What is cos 30? Root 3 by 2. That is equation number 2. Now if you divide these two, we have B2 here. If you divide these two, on the left we will be having 4 by 3, and on the right we will be having a square root of B2 root 3 times root 3 root 2 and divided by B1 times 2. Okay, and from here just square this and you will find B1 by B2 will be very nearly equal to 0.7. So B is the correct choice. Okay. Next question. In this question, they say there is a fighter plane whose length is 20 meter, wing span means from one tip to other tip, the total outer length of wing is 15 meter and height is 5 meter, and it is flying towards east over Delhi. Its speed is given, the Earth's magnetic field over Delhi is given, and declination angle we have to assume almost 0, and dip is also given. Okay, so let me draw the situation. Suppose we are looking at top view. From top view we see the length of plane or the plane is 20 meter, and the width is 15 meter and the length is 20 meter. It is flying towards east and with a velocity of 240 meter per second. If we observe this plane from the right side, means if we observe this plane looking towards west, we will look at its front view, and there we will be looking at the 15 meter length, and we will also look at its height, which is 5 meters only. Okay. As the angle of declination is almost 0, this is east-west line, will be having the magnetic field of Earth in this plane, because this is north-south line and angle of declination is almost 0. Okay, so the magnetic field of Earth will be in this plane, and if magnetic field is of Earth in this plane, suppose here we have north, here we have south, so the magnetic fields horizontal component would be like this, BH, and the vertical component of magnetic field will be like this inside BV. Right. Let me draw this in front view also. This is BH and this is BV, and here we have angle of dip. Okay. Now they are saying that the voltage developed is VB. Where the voltage developed is VB? Yes, VB is the voltage developed between the lower and upper side of the plane. Okay. So let us calculate VB. See, this is the lower and upper side of the plane, and this length is 5 meters. It is moving towards U, so it is moving in this direction towards east. See, length is vertical, the velocity is like this, and BH is perpendicular to both. So I think you remember, if all BVL are perpendicular, we just learnt in EMI, if all BVL are perpendicular, the EMF developed is BVL. Okay, so here the length is vertical, the velocity is towards you, and BH is like this. So in this length, there will be no induced EMF because of BV, because BV and length are in same direction or same line, they are parallel. So the VB will be equal to BH, V and height, which is 5. As BH can be written as the net magnetic field of Earth times cos theta. So net magnetic field of Earth is this 5 times 10 to the power minus 5. So we have BH as 5 times 10 to the power minus 5. V cos theta, we know the value of sin theta, we can easily calculate cos theta. The velocity is 240 meters and the length is 5. Okay. And if you calculate this properly, you will get the numerical value very close to almost 44.7 something. So it will be very close to 45. Yes, 45 times 10 to the power minus 3. It is actually 44.78 something. So we have assumed it the value as 45 times 10 to the power minus 3 millivolt. Okay. So VB is 45 times. So we have VB equals to 45 in option B and D. So these two, one of these two is correct. Now we will check what is VW. See, actually in both options we have VW as 120. So there is no need to check the magnitude of VW. We have to just check the direction of VW. Okay. So suppose we have a pilot here, and if pilot here is flying towards east, his left hand will be here and right hand will be on this side. And as the VW is the EMF induced across the wings, the BH has no effect because the length of wings is parallel to BH. If length and BH or length or B is parallel, there is no induced EMF, right? The induced EMF is developed when none of the two vectors BV, L are parallel. Okay. So obviously on this length, the EMF induced will be because of BV. The EMF induced in this length will be because of BV, because this length is like this, velocity like this, and BV perpendicular to both. So all three are perpendicular to each other. So actually VW will be equal to the length BV times velocity times length is 15 meter. You calculate it, you will get approximately 120 millivolt. Let us see which end is positive. Okay. So actually the velocity is towards right, and magnetic field is inside. If you do V cross B, if you turn your fingers of right hand from V cross B, the thumb is pointing upward. So thumb is pointing upward. You know, I think in the direction of V cross B, we get positive end. So this will be positive end, this will be negative end. So obviously the driver's left hand side's end is positive as compared to the right hand side. So let us check. We have in this D, the left side of pilot at higher voltage than the right hand side. So D is the perfect choice for this. So that was all about Earth's magnetic field and permanent magnets. I'll also teach you in detail the magnetism and matter, or the magnetic properties of matter, but that I'll cover in the next chapter with alternating current. That will make the lectures more uniform in terms of time. Okay, so thanks for today. Keep watching. I'll again say watch these videos in steps of 1 hour or 1.5 hours, so it will not tire you. Okay, and these are very important questions, so you have to learn them by heart. Okay, thank you so much.